Somewhere in Indonesia 74,000 years ago, a mountain didn't just erupt. It detonated with a force so massive it makes every volcanic eruption in recorded human history look like a struck match. And when the ash finally settled, some scientists believe humanity had been pushed to the edge of a cliff so narrow, so precarious, that the entire future of our species came down to maybe 10,000 people. Maybe fewer, scattered, isolated, barely holding on. Think about that for a second. 10,000 people. That's smaller than most high schools' entire alumni network. That's fewer people than fit in a mid-sized concert venue. And according to one theory, that's all that stood between humanity existing and humanity simply not. This is the Toba catastrophe theory, and it's one of the most gripping, most debated ideas in all of human evolution. The claim is staggering. A supervolcano so powerful it choked the atmosphere with ash and sulfur, triggered years of volcanic winter, collapsed food chains across entire continents, and nearly erased the human story before it really got going. If true, every single person alive today, all 8 billion of us, would be descended from a tiny population of survivors who somehow made it through the worst environmental disaster our species has ever faced. But here's where it gets interesting. Not everyone agrees this happened the way the theory describes. Some scientists look at the same ash layers, the same genetic data, the same archaeological sites, and come away with a completely different conclusion. Maybe Toba wasn't an extinction event at all. Maybe early humans barely noticed. Maybe the real story isn't about a species clinging to survival, but about how resilient, how adaptable, how surprisingly tough our ancestors actually were. So which is it? Did a volcano in Indonesia nearly reset the entire human timeline? Or has decades of scientific storytelling turned a serious but survivable disaster into something far more dramatic than the evidence actually supports? That's exactly what we're digging into today. And I promise you, the deeper you go into this story, the stranger and more fascinating it gets. We're going to walk through the geology of the eruption itself, one of the largest in the last 2 million years. We're going to look at the genetic bottleneck theory and where that number, 10,000 survivors, actually came from and whether it holds up under scrutiny. We're going to examine ice cores, ocean sediments, and ash deposits that let scientists reconstruct what the climate might have looked like in the years after the eruption. And we're going to look at something that might surprise you. Archaeological sites in India where stone tools have been found both beneath and above the volcanic ash layer, suggesting that maybe, just maybe, life went on. By the end of this, you'll have a clearer picture than almost anyone talking about this topic online, because we're not just going to tell you the dramatic version. We're going to show you the evidence, the uncertainty, and the genuine scientific debate that's still unfolding right now. Before we get into it, if you're listening to this late at night, getting ready to drift off, or maybe on a morning commute somewhere across the world, I'd love to know where you're tuning in from and what time it is there. I check the comments constantly, and there's something genuinely amazing about seeing someone in Manila at sunrise, someone in Toronto at midnight, someone in Cape Town on their lunch break, all listening to the same story about a volcano that may have shaped every single one of us. So drop a comment, let me know where you are, and if you want the easiest way to catch every episode the moment it drops, follow the show on Spotify. Listening there helps more than you'd think, and if you're enjoying what you hear, a 5-star review goes a long way. Links in the description. Now, let's rewind the clock. Because to understand what happened at Toba, we first need to understand just how fragile human life already was before that mountain ever erupted. Let's go back before the ash, before the eruption, before anyone knew a mountain in Indonesia was even capable of what it was about to do. Let's talk about what the world actually looked like 74,000 years ago, because honestly, most people picture this completely wrong. There were no cities, no farms, No permanent settlements with populations in the thousands. Homo sapiens had already existed for over 100,000 years by this point, but civilization in the way we think about it today simply didn't exist yet. There was no writing, no agriculture, no fixed addresses. What existed instead were small bands of people, probably somewhere between 20 and 100 individuals, moving across the landscape following food, water, and seasons. That was life. That was the entire infrastructure of being human. And this wasn't unique to Africa. By this point in history, our species wasn't the only human story unfolding on the planet. Neanderthals were already thriving across Europe, and parts of Western Asia hunting massive Ice Age animals with tools they'd spent tens of thousands of years perfecting. In Asia, the Denisovans, a group we still know frustratingly little about, were adapting to environments ranging from frigid mountain plateaus to tropical islands. There's even growing evidence of other human relatives, smaller, more mysterious populations like Homo floresiensis in Indonesia, coexisting during roughly the same window of time. The world 74,000 years ago wasn't a story about one triumphant species marching toward dominance. It was a crowded evolutionary experiment, multiple human species, sharing a planet, sometimes overlapping, sometimes competing, occasionally even interbreeding when their paths crossed. But here's the thing that mattered most for what was about to happen. None of these populations were large. Not by our standards, not by any standard really. Best estimates suggest the total global population of Homo sapiens at this point might have been somewhere in the tens of thousands, maybe more, maybe considerably less. We genuinely don't know the exact number, and anyone who tells you they do is guessing with more confidence than the evidence allows. But even at the high end, we're talking about a species that could have fit, with room to spare, into a single mid-sized modern city. Now stretch that population across an entire continent. Across savannas, coastlines, river valleys and mountain ranges spanning thousands of miles. Suddenly that number doesn't feel so reassuring anymore. It feels fragile, precarious, like a handful of matches scattered across a football field, each one representing a tiny flicker of a group trying to survive. This is the part that's easy to miss when you first hear about Toba. We tend to imagine early humans the way we imagine ourselves, connected, numerous, resilient, because there are billions of us. But 74,000 years ago, humanity wasn't a single interconnected network with the buffer of global population size. It was a patchwork, isolated pockets, groups who might not have known other groups existed just a few hundred miles away. And that isolation, that smallness, is exactly what made this era of human history so vulnerable to sudden catastrophic change. Think about how a modern disaster plays out. A hurricane hits Florida, and the rest of the country sends supplies, personnel, support. A drought devastates one region, and food gets shipped in from somewhere else entirely. We have redundancy built into everything: multiple regions, multiple economies, multiple fallback systems. If disaster strikes one place, the species survives because the species is enormous and spread across nearly every corner of the planet. None of that existed 74,000 years ago. If a single group of 30 people ran into a multi-year drought, there was no emergency shipment of food arriving from 3 states over. There was no radio call for help. There was just whatever they could find, hunt or gather within walking distance, and whatever knowledge had been passed down to them by their parents and grandparents. If the environment turned against them hard enough, for long enough, that group simply vanished. Not metaphorically, actually vanished. Their genetic line ending, their stories forgotten, their existence reduced to nothing more than maybe, someday, a scatter of stone tools an archaeologist might stumble across tens of thousands of years later. Multiply that vulnerability across dozens or hundreds of scattered bands, and you start to understand why the concept of a species-threatening bottleneck isn't as far-fetched as it might initially sound. It's not that early humans were weak or poorly adapted. Quite the opposite. They were remarkably resourceful, capable of surviving in deserts, forests, coastlines, and grasslands, using nothing but stone tools, fire, and cooperation. But resourcefulness only gets you so far when the environmental rug gets pulled out from under you abruptly, and on a scale beyond anything your ancestors had ever adapted to handle. This is really the key thing to understand before we get into Toba itself. What could realistically be reset 74,000 years ago wasn't civilization in the sense of cities crumbling or empires collapsing. There were no empires, no cities, nothing built up that could visibly fall down. What was actually at risk was something far more basic, and in some ways far more terrifying. The continued existence of the species itself, not a setback. Not a dark age, an ending. If enough of those scattered bands were wiped out simultaneously, if the disaster was severe enough and widespread enough, there might not have been enough surviving groups left to maintain genetic diversity, to keep the overall population from collapsing into something dangerously small and inbred, or in the worst case, to keep the species going at all. This is precisely why a single volcanic event, however catastrophic, has become one of the most debated potential threats in our entire evolutionary history. Not because it could destroy buildings or infrastructure, there wasn't any yet, but because it might have been powerful enough to destroy the very thing keeping humanity alive, a functioning, breeding, geographically distributed population large enough to persist. So picture the world just before Toba erupted. Small bands of Homo sapiens scattered across Africa, coexisting on the same planet as Neanderthals in Europe, Denisovans in Asia, maybe other human relatives in isolated pockets like Indonesia. No cities, no writing, no safety nets beyond the people standing next to you and the land you happen to be standing on. A species that had survived for over 100,000 years through nothing but adaptability, cooperation, and sheer stubborn endurance. And then, somewhere in what is now Sumatra, deep beneath a mountain, nobody was watching. Pressure that had been building for hundreds of thousands of years was about to find its way out. Today, that place is called Lake Toba. It sits high in the mountains of northern Sumatra, Indonesia. A vast blue body of water surrounded by steep green ridges and volcanic peaks. If you saw it from a distance, you might think it was just another beautiful mountain lake. Peaceful, ancient, the kind of place people visit to escape cities and take photographs of the view. But Lake Toba is not really a lake in the ordinary sense. It is a scar more than 60 miles long, roughly 20 miles wide, carved into the earth by one of the largest volcanic eruptions known from the entire history of our species. The lake fills a giant collapsed basin called a caldera. And beneath that water, beneath the fishing boats and the quiet shorelines, lies the broken remnant of a volcanic system that once tore open with enough force to send ash across much of Asia and beyond. To understand why Toba became so central to theories about human survival, you have to understand what kind of volcano this was. Because when most of us hear the word volcano, we picture something like Mount Etna, Mount St. Helens, or Hawaii's Kilauea. A mountain with lava flowing down its slopes, smoke rising from a crater. Maybe an explosion, maybe an evacuation zone, but still something that looks like a mountain erupting. Toba was something else entirely. Ordinary eruptions can be devastating, of course. Lava can burn towns, ash can collapse roofs, mud flows can bury valleys. But many eruptions are relatively small in global terms. They release pressure from a volcanic system without fundamentally changing the planet's climate. A powerful eruption might affect a region, maybe disrupt air travel across a continent, maybe darken the sky for days or weeks. A supereruption operates on a scale that is almost hard to imagine. Instead of a single vent coughing out lava and ash, you have an enormous reservoir of molten rock building beneath the surface over tens of thousands, sometimes hundreds of thousands of years. This is called a magma chamber, although chamber makes it sound too neat, too contained. It isn't usually a giant underground cave full of liquid fire. It is more like a vast zone of hot, partly molten rock, crystals, gases and magma threaded through the crust beneath a volcanic region. And the crucial ingredient is gas. Deep underground, under immense pressure, gases remain dissolved in magma the way carbon dioxide stays dissolved in a sealed bottle of soda. But when magma begins rising toward the surface, pressure drops. The gases expand, bubbles form. More bubbles mean more expansion. More expansion shatters the magma into tiny fragments. At a certain point, the system doesn't just ooze lava, it detonates. That is the difference between molten rock quietly reaching the surface and a mountain-scale explosion turning rock into airborne ash. At Toba, the eruption did not merely open a hole in the ground. It emptied so much material from beneath the surface that the land above could no longer support its own weight. The crust collapsed inward. Imagine removing the foundation beneath an enormous building, except the building is an entire section of landscape, miles across. The ground fractures, drops and folds into the void left by the escaping magma. What remains is a colossal basin, a caldera. Lake Toba exists because the earth collapsed after the eruption. And in the centre of that lake sits Samosir Island, itself part of the story. It is not simply an island that happened to be in the water. It is uplifted land within the caldera system, shaped by the continued restless movement of rock beneath the surface. Even after an eruption on this scale, the planet does not just settle down and forget. The ground adjusts, magma shifts, faults move, landscapes rise and fall over thousands of years. The whole region is part of the Sunda Arc, a chain of volcanoes created by one of the most violent processes on Earth, subduction. Beneath Indonesia, the Indo-Australian tectonic plate is being forced under the Eurasian plate. As one plate descends into the mantle, water and minerals help trigger melting in the rock above it. That melt rises. Volcanoes form. Indonesia has hundreds of them. But Toba was unusually large because its volcanic system had accumulated an extraordinary volume of magma over a very long time. It had erupted before. The landscape around the modern lake preserves evidence of multiple major eruptions stretching back hundreds of thousands of years. Toba was not a single one-time accident. It was a long-lived volcanic complex, repeatedly recharged from below, repeatedly reshaped by eruptions. Then, around 74,000 years ago, came its most famous event, the youngest Toba Tuff eruption. Tuff is the geological name for rock made from volcanic ash that has settled, compacted and hardened. The name sounds technical, almost harmless, but the youngest Toba Tuff is really the signature left behind by an explosion so immense that geologists can trace its ash deposits thousands of miles from the source. This is where the story starts becoming unsettling. When a supereruption occurs, the immediate danger is not limited to lava. In fact, lava may be almost beside the point. The most lethal forces are often pyroclastic flows, ground-hugging avalanches of scorching gas, ash, rock fragments, and debris racing outward at terrifying speeds. These are not clouds drifting gently through the air. They are hurricanes of pulverized rock, hot enough to incinerate vegetation and deadly enough to erase everything in their path. Near Toba, pyroclastic flows would have swept across the surrounding landscape, filling valleys and burying huge areas beneath thick volcanic deposits. Forests, rivers, animals, and any human communities unlucky enough to be close to the eruption zone would have faced almost no chance of escape. But the local destruction was only the first layer. Above the eruption, a column of ash and gas would have punched high into the atmosphere. Not just smoke rising above a mountain, but a towering plume reaching into the upper atmosphere, where winds can carry material across enormous distances. Fine ash spread outward over land and sea. Larger particles fell closer to the volcano, blanketing parts of Indonesia and the Indian subcontinent. Smaller particles travelled farther, settling in layers that modern researchers can identify by their chemistry. That chemistry matters because it gives scientists a timestamp. Across southern Asia, archaeologists have found layers of ash associated with Toba. In some places, stone tools lie beneath the ash. In others, tools appear above it. Those thin, pale layers, buried in soil and sediment for tens of thousands of years, have become one of the most important pieces of evidence in the debate over whether Toba nearly destroyed human populations or whether people endured the disaster more successfully than the dramatic version of the story suggests. But before we get to the people, there is another threat to consider. The one that made Toba famous far beyond geology. A supereruption does not just throw ash onto the ground. It can inject sulfur gases high into the stratosphere. There, those gases can form sulfate aerosols, tiny reflective particles that bounce some incoming sunlight back into space. Enough of them in theory and the planet cools. Growing seasons shorten. Rainfall patterns shift. Droughts intensify in some regions. Ecosystems already living close to the edge begin to fail. This is the volcanic winter hypothesis, and it is why Toba became more than a story about one terrible eruption in Indonesia. It became a possible explanation for a global human crisis. If the eruption was large enough, if enough sulfur reached the stratosphere, if cooling lasted long enough, then the consequences might have reached far beyond Sumatra. Not as a wall of fire moving across continents, but as something potentially worse for scattered hunter-gatherer populations. Years of unstable weather, damaged food webs, failing animal migrations, weakened plant growth, and landscapes that no longer produced enough food to sustain small human groups. That is the chain of events researchers began to imagine. Eruption, ash, sunlight blocked or reflected, climate disrupted, resources collapse, human numbers crash. It is a powerful theory, almost too powerful. The kind of explanation that seems to tie every mystery into one neat story. A giant volcano erupts, humanity nearly disappears, and the survivors become the ancestors of everyone alive today. But nature is rarely that neat. The size of the eruption is not really in doubt. Toba was colossal, the caldera is there, the ash is there, the deposits are there. What remains uncertain is what that eruption actually did to climate, how long those effects lasted, how differently they played out from one region to another, and whether Homo sapiens really came within a few thousand people of extinction because of it. Lake Toba gives us the crater. The ash gives us the date, but neither one by itself tells us how many humans died. For that, we have to go back to the moment the volcano broke open and follow what it sent into the sky. Around 74,000 years ago, the pressure finally broke. The best current estimates place the youngest Toba Tuff eruption at roughly 73,900 years ago, give or take a margin of error that matters to geologists but would have meant nothing to anyone alive at the time. No warning broadcast, no evacuation route, no way to understand what was building beneath the forests and mountains of northern Sumatra. At some point, the ground began to rupture across a vast volcanic system. Magma that had been trapped under pressure started forcing its way upward. As it rose, dissolved gases expanded violently. The magma shattered into fragments of pumice, ash, and rock. Then the eruption accelerated beyond anything humans had ever witnessed. This was not one explosion in the ordinary sense. It was probably a sustained sequence of colossal explosive events, perhaps unfolding over days or weeks, though the exact duration remains uncertain. The evidence is buried in the deposits. Enormous sheets of volcanic material, layers of ash, welded rock, and pyroclastic debris spread across the region. The eruption is known as the youngest Toba Tuff because it was the most recent of Toba's giant caldera-forming eruptions, and by almost any measure, it was among the largest volcanic events known in the last few million years. Volcanologists use something called the Volcanic Explosivity Index, or VEI, to compare eruptions. It works a little like the scale used for earthquakes, except instead of measuring shaking, it measures explosive output, how much material was erupted, how high the plume rose, and how widespread the deposits became. A VI4 eruption is considered large. Mount St. Helens in 1980 was a VI5. Krakatoa in 1883, the eruption that produced tsunamis, explosions heard thousands of miles away, and global atmospheric effects was a VII6. Toba is generally classified as VI8. That is the highest category on the scale. A VI8 eruption involves more than 1,000 cubic kilometers of erupted material. To picture that, imagine taking enough rock to cover an entire large country beneath a layer of volcanic debris. Then imagine blasting much of it high into the atmosphere, while the rest races across the ground as searing avalanches of ash and gas. But even here, there is an important distinction. Scientists agree Toba was enormous. The caldera itself, the deposits around Sumatra, and the ash layers found far from Indonesia make that unavoidable. What remains debated is exactly how enormous. Some estimates suggest the eruption expelled thousands of cubic kilometers of magma when measured as dense rock equivalent. Others give larger or smaller figures depending on whether they count loose ash, compacted deposits, material that flowed across the ground, or magma before it expanded into pumice and ash. You will sometimes see a single number presented as if it is exact. It isn't an eruption 74,000 years old does not leave behind a receipt. What the geology can tell us is simpler and more frightening. Toba removed enough material from beneath northern Sumatra that a huge part of the surface collapsed. The result was a caldera roughly the size of a major metropolitan region. Pyroclastic flows poured outward from the eruption zone, moving across the landscape with immense heat and destructive force. These flows are mixtures of gas, ash, pumice, and broken rock, dense enough to hug the ground and fast enough that escape is often impossible close to the source. Near Toba, the world would have been erased. Forests would have been flattened, burned, and buried. Rivers may have been choked with ash and debris. Valleys would have filled beneath thick volcanic deposits. Animals caught in the path of the flows would have had little chance. Any human groups living near the eruption zone would have faced a disaster far beyond anything their knowledge, tools, or social networks could have prepared them for. And this is one point that does not depend on the volcanic winter theory. You do not need to assume a decade of global cooling to understand that Toba was catastrophic in Sumatra. The local devastation is built into the landscape itself. But Toba did not keep its violence local. As pyroclastic flows raced across the ground, another part of the eruption was moving in the opposite direction. A towering column of ash, gas, and pumice rose upward through the atmosphere. The exact height is uncertain. Reconstructing an ancient plume is difficult, especially one from an eruption this large. But it almost certainly reached altitudes where powerful winds could take over, carrying fine volcanic material far beyond Indonesia. And once the ash entered those high-altitude winds, it became a continental problem. The largest fragments fell first, mostly near the volcano. Heavy pumice and coarse ash blanketed parts of Sumatra and the surrounding region. Farther away, particles became finer. The layer thinned. But it kept going. Across the Indian subcontinent, researchers have identified ash deposits chemically linked to Toba. In some places, the ash layer is thick enough to be obvious in the ground, a pale band preserved between older and younger sediments. In others, it is thinner, mixed into soil, river deposits, or ancient lake beds. But the chemical fingerprint can still reveal where it came from. Volcanic glass has its own signature. The proportions of elements locked inside tiny shards can be compared with material from Toba itself. When those fingerprints match, geologists can trace the path of an eruption across thousands of miles. That is how we know this was not just a regional blast. Toba ash has been identified across South Asia, through parts of Southeast Asia, and in marine sediment cores from the Indian Ocean. Traces have been reported much farther away as well. Although the farther from the volcano you go, the harder it becomes to separate secure evidence from disputed identifications. Ash can be reworked by wind and water. Sediments can be disturbed. Similar volcanic deposits can sometimes be confused with one another. Still, the broad pattern is clear. A massive cloud spread westward and northwestward from Sumatra, crossing sea and land, falling over landscapes occupied by animals, plants, and at least some human populations. Imagine what that would have looked like from the ground in India, hundreds or even thousands of miles away. Not a fireball on the horizon, not lava coming over a ridge. Something stranger, a dimming sky, fine dust settling onto water, leaves, skin and food, ash gathering in hollows and drifting into camps. The immediate effects would have depended on distance, wind direction, rainfall, and the thickness of the deposit. For some communities, it may have been a severe disruption. For others, it may have been a deadly local crisis. And for places outside the main ash path, the physical fallout may have been limited. That unevenness matters. The map of ash is not a map of death. A thick ash deposit does not automatically tell us every living thing beneath it died. A thin deposit does not prove conditions were harmless. And the presence of Toba ash in a particular region does not tell us whether humans were there at that exact moment, or how they responded if they were. But it does give us something incredibly valuable, a marker in time. The youngest Toba Tuff is like a line drawn through the archaeological record. Below it are traces of life before the eruption. Above it are traces of life after. If we can find tools, hearths, animal bones, and campsites on both sides of that line, then we can begin asking the question that turns Toba from geology into human history. Did people vanish? Did they survive in isolated refuges? Did some groups collapse while others adapted? For now, though, stay with the eruption itself, because ash was only part of what Toba launched into the sky. Mixed into that plume were volcanic gases, especially sulfur-bearing gases. And unlike ash, which mostly falls out relatively quickly, sulfur compounds can reach the stratosphere and remain there long enough to alter the amount of sunlight reaching Earth's surface. That is where the story moves from a catastrophe in Sumatra to a possible crisis for the entire planet. But before we follow those gases into the stratosphere, there is another trail to follow. A trail so fine that in many places you cannot see it with the naked eye. It is made of broken glass. When magma erupts violently, it does not simply become dust. Much of it is blasted apart so quickly that it cools into tiny fragments of volcanic glass. Under a microscope, these shards can look like jagged splinters, curved bubbles or transparent flakes with razor-sharp edges. They are the frozen remains of an eruption cloud. Scientists call very small, often invisible deposits of this material cryptotephra. Tephra is the general word for volcanic material thrown into the air, ash, pumice, and fragments of rock. Crypto means hidden, so cryptotephra is hidden ash, microscopic evidence of an eruption preserved in places where no obvious grey layer remains. And this is how Toba's reach becomes even more extraordinary. A thick ash bed is easy to notice. A geologist digging through a riverbank, lakebed, or archaeological trench may find a pale band of volcanic material sitting between darker layers of soil. It can be centimetres thick, sometimes more. It looks like an interruption in the landscape, a sudden geological event frozen in place. But most of the ash from a distant eruption does not survive in that clean, dramatic form. Rain can wash it into streams, wind can scatter it. Roots, burrowing animals, floods, and thousands of years of soil formation can churn it into surrounding sediment. A layer that was once visible may become diluted until it disappears completely to the human eye. That does not mean the eruption left no trace. Researchers take samples from sediments, sometimes gram by gram, and process them in laboratories. They wash away clays, separate particles by density, and search for microscopic glass shards. In lake cores, peat bogs, marine sediments, and ancient floodplains, they may find only a handful of shards in an entire sample. But a handful can be enough, because volcanic eruptions have chemical signatures. Every magma system forms under its own conditions. Its chemistry reflects the rocks it melted, the minerals it interacted with, and the long underground history of the molten material before it erupted. The glass shards produced by that magma preserve part of this chemical identity. Scientists measure elements such as silicon, aluminum, iron, sodium, potassium, calcium, and titanium. They can use powerful instruments to analyze individual shards, sometimes ones smaller than the width of a human hair. Then they compare those results with known samples from Toba. It is a little like forensic science. Imagine finding tiny fragments of coloured glass scattered across cities thousands of miles apart. They may all look similar at first, but under precise analysis, each one contains a unique recipe. The same proportions, the same chemical pattern, the same source. When shards in India or the Indian Ocean match the chemical fingerprint of the youngest Toba tuff, they become more than dust. They become evidence of a single eruption reaching far beyond Sumatra. That evidence has been found across a huge area. In South Asia, Toba ash occurs at sites stretching across the Indian subcontinent. In some regions, especially farther south and closer to the likely path of the plume, ash deposits can be substantial. In other places, the signal is thin, patchy, or visible only under a microscope. Marine sediment cores from the Bay of Bengal and the wider Indian Ocean preserve another version of the same event, a pulse of volcanic material settling through the water and onto the seafloor. The ocean, in a way, became an archive. Ash fell onto its surface, mixed into the upper waters, and eventually sank. Layer by layer, mud accumulated over it. Tens of thousands of years later, scientists drill down through that mud and encounter the Toba horizon, a narrow band marking the moment one volcano disturbed an enormous part of the region. The pattern of these deposits helps reconstruct the direction of the fallout. Near the volcano, the deposits are thick because the largest and heaviest fragments fall quickly. Pumice, coarse ash, and rock fragments do not stay in the atmosphere for long. Gravity pulls them down. This is why the landscape around Toba bears the most obvious scars. Farther away, the particles become finer. Fine ash can remain suspended much longer, carried by winds across seas and continents. The ash layer usually thins with distance, but not in a perfectly even circle. Wind direction matters, so does the height of the plume. Rain can pull particles out of the atmosphere rapidly in one region, while leaving another relatively untouched. Mountains can redirect air currents. Rivers can later concentrate ash in one valley and remove it from another. So ash thickness is not just a measure of distance. It is a clue to a much messier story. A thick deposit may indicate proximity to the volcano. Yes. But it may also reflect where the main ash cloud travelled, where rain scrubbed ash from the sky, or where sediment later collected and preserved it. A thin deposit might mean the location was far away, or it might mean the original layer was eroded, mixed, or never preserved well in the first place. This is why maps of Toba fallout come with uncertainty. Scientists can identify the broad outline, an eruption cloud moving across Southeast Asia, the Indian Ocean, and South Asia. But the precise thickness of ash at every location, on every day of the eruption, is beyond recovery. The ground has been changing for 74,000 years. Coastlines moved, rivers shifted, forests grew and vanished. Human activity itself disturbed ancient sediments. Still, even the imperfect map is startling. Toba did not merely throw ash over its own island. It marked landscapes across continents. It left microscopic glass in distant sediments. It created a timestamp that can be recognized from Sumatra to India and beneath the Indian Ocean. And that timestamp is incredibly useful. If an archaeological site contains stone tools beneath Toba ash, those tools were made before the eruption. If more tools appear in sediments above the ash, they were made after. That sounds simple, but it gives researchers a rare chance to test one of the biggest claims ever made about Toba. Did the eruption wipe out human populations across South Asia? For a long time it was tempting to see the ash layer as an answer by itself. Massive eruption, ash across India, therefore devastation, therefore empty landscapes. But geology does not work that way, and neither does human survival. Finding volcanic ash at a site proves that ash arrived there. It does not prove that every human group in the region died. It does not tell us how long the ashfall lasted at that exact location. It does not tell us whether people fled, sheltered, moved toward rivers, changed their diet, or returned after a short disruption. It does not even prove that people were present at that particular spot when the ash fell. An ash layer is evidence of hazard, not a census. A few centimeters of ash could be disastrous if it poisoned water sources, smothered edible plants, or disrupted animal migrations during an already difficult season. But the same thickness in another setting might be survivable, especially for mobile groups able to move through a large territory. And even a thick ash deposit does not automatically mean instant extinction. Humans are not trees rooted in one place. They can leave. The real question is not whether Toba ash crossed continents. It did. The question is what happened to the living world after it landed. Did ash choke ecosystems for months? Did it trigger food shortages? Did it force people into smaller refuges? Or did many populations endure the fallout and continue making tools, hunting animals, and moving across the same landscapes as before? To answer that, we have to look beyond the glass shards and into the atmosphere itself. Because Toba's most dangerous legacy may not have been what fell to earth. It may have been what stayed in the sky. What stayed in the sky was gas. And of all the gases released by a giant volcanic eruption, one matters more than almost any other when it comes to climate. Sulfur dioxide. Deep beneath a volcano, sulfur can be dissolved inside molten rock. When that magma rises and pressure suddenly drops, gases escape violently, expanding like a shaken bottle being opened all at once. Carbon dioxide, water vapour, chlorine compounds and sulfur dioxide can be blasted upward with the ash. Most volcanic material falls back down. The heavy fragments fall first. Then coarse ash, then finer ash drifting across the landscape. But if an eruption column rises high enough, some of its gases can cross into the stratosphere. the layer of atmosphere above most clouds and weather, that changes everything. Down near the ground, rain can wash sulfur dioxide out of the air relatively quickly. But in the stratosphere, there is almost no rain. The gas can remain there long enough to undergo a chemical transformation. It reacts with water vapor and oxygen, forming tiny droplets and particles of sulfuric acid called sulfate aerosols. These particles are incredibly small, much smaller than grains of ash. And because they are so small, they can spread around the planet on high-altitude winds. Then they begin reflecting sunlight back into space. Not enough to turn day into night, not enough to freeze the entire planet overnight, but enough potentially to reduce the amount of solar energy reaching Earth's surface. Less sunlight means cooler land, cooler oceans, weaker evaporation, and disrupted rainfall patterns. This is the basic idea behind the volcanic winter hypothesis. A massive eruption, huge sulfur release, a veil of sulfate aerosols in the stratosphere, sunlight reduced, temperatures fall, rainfall shifts or weakens, ecosystems begin to fail, and if the eruption was Toba, the consequences could have been enormous. Think about what happens when a region receives less sunlight for one growing season. Plants grow more slowly, some fail to flower or produce seeds. Others become more vulnerable to frost, disease, or drought. In cold regions, a shorter warm season can mean less grass, fewer berries, fewer insects, and weaker animal herds heading into winter. Now extend that stress across multiple years. Herbivores suffer first because their food supply declines. Then predators suffer because the herbivores become scarce. Rivers may run lower if rainfall weakens. Lakes can shrink. Forests can change. Grasslands can dry out. Migration routes that animals followed for generations may no longer provide enough food or water. For humans living in that world, the disaster would not need to arrive as a wall of ash. It could arrive as absence. No herd at the usual crossing point. No fruit in a grove that normally produces every year. Fewer fish in a shrinking wetland, a water hole gone dry. A hunting territory suddenly supporting half as many animals as before. People sometimes describe volcanic winters in terms of crop failure. And that makes sense when we talk about historical farming societies. But 74,000 years ago, humans did not have wheat fields waiting to be destroyed. They were hunter-gatherers. No farms, no granaries. No stored harvest capable of carrying an entire village through several failed seasons. But that did not make them immune. Hunter-gatherers depend on ecosystems with an intimacy most modern people can barely imagine. They depend on the timing of rains, the fruiting of plants, the movement of game, the survival of edible roots, the availability of shellfish, fish, birds, honey, seeds and water. Their food supply was diverse, which could make them resilient. But it was also completely tied to the living landscape. If the landscape faltered, people faltered with it. A volcanic winter would not have killed every group in the same way. Some may have faced cold, others drought, others failed monsoons. Some coastal groups might have found refuge in marine foods. Some river valleys might have remained productive while nearby uplands became desperate. But across a large enough region, years of ecological disruption could force groups to move, compete, abandon territories, or watch their numbers fall. This was the argument that made Toba famous. Not simply that it was a giant eruption. Plenty of eruptions are giant by human standards. The claim was that Toba was so immense that it may have pushed Earth's climate into a severe volcanic winter lasting years, perhaps with knock-on effects lasting decades. The theory became especially influential in the 1990s, when researchers began connecting three pieces of evidence. First, the scale of the youngest Toba Tuff eruption. It was one of the largest eruptions of the last several million years, producing an extraordinary volume of volcanic material and leaving deposits across South Asia and the Indian Ocean. Second, the known climate effects of smaller eruptions. And third, genetic studies suggesting that modern humans may have passed through a population bottleneck sometime in the deep past. Put those together, and the story seemed almost unavoidable. Toba erupts, the planet cools, human populations crash. Perhaps only a few thousand breeding individuals survive in scattered refuges. Everyone alive today descends from those survivors. It is a powerful story, but powerful stories can get ahead of the evidence. To understand why scientists took the idea seriously in the first place, look at a much smaller eruption, Tambora, in Indonesia in 1815. Tambora was nowhere near the scale of Toba, yet its eruption injected enough sulfur into the stratosphere to cool the climate noticeably. The following year became known in parts of the northern hemisphere as the year without a summer. Frost struck during months when crops should have been growing. Rainfall patterns shifted. Harvests failed across parts of Europe and North America. Food prices rose. Famine and hardship followed. One eruption in Indonesia disrupted weather and food systems an ocean away. Tambora showed that volcanoes can reach across the planet. They do not need lava flows to touch distant populations. They can alter sunlight, temperature and rainfall from thousands of miles away. So imagine scaling that mechanism up. If Toba released vastly more sulfur dioxide than Tambora, perhaps its aerosol veil was thicker, longer lasting and more globally disruptive. Perhaps temperatures dropped by several degrees in some regions. Perhaps monsoon systems weakened. Perhaps the planet entered a period of severe cooling that lasted not months but years. Some early estimates were dramatic. They proposed global cooling of several degrees Celsius, with much sharper drops in certain areas. They suggested that Toba's effects might have lasted 6 years, 10 years, even longer when ecological consequences were included. A cold spell does not end the moment the aerosols disappear. Animal populations need time to recover. Forests need time to regrow. Drought-stricken landscapes can remain fragile for generations. That is the key distinction. The volcanic winter itself may have been relatively brief in geological terms. But a few bad years can be catastrophic when people live close to the edge of survival. And the after-effects could stretch much further. Imagine a small human band already dealing with seasonal hunger. A few children die during a hard, dry season. An older hunter is injured. A neighbouring group controls the nearest reliable water source. Then the climate shifts. The rains fail twice. The game animals thin out. Wild plants produce less food. Suddenly, a population does not need to be killed in one instant to disappear. It can simply fail to replace itself. That is what made the Toba hypothesis so frightening. It offered a mechanism for a slow-motion catastrophe. Not one day of fire, but years of dimmer skies, colder weather, failing rains, empty hunting grounds, and human communities shrinking one death at a time. But a mechanism is not proof. Toba clearly erupted. Its ash clearly travelled across continents. Sulfate aerosols from volcanoes clearly can cool the climate. The unresolved question is scale. How much sulfur reached the stratosphere? How long did it remain there? How strongly did global temperatures and monsoons respond? And did the disruption line up with an actual collapse in human populations? Those questions turn out to be much harder than they sound. Because the size of an eruption does not automatically tell us the severity of its climatic aftermath. So how do you measure a winter that happened 74,000 years ago? You cannot check a thermometer. You cannot read a weather report. You cannot look at a harvest record because there were no written records, no farms, no cities, no one recording that the rains came late, and the herds never returned. Instead, scientists have to reconstruct Toba's climate impact from fragments. Ice cores, ocean mud, ancient pollen, chemical traces, tiny shells from microscopic sea creatures, computer models built from physics, chemistry, and educated assumptions about an atmosphere that no longer exists. Each line of evidence offers part of the picture, and none of them offers the whole thing. Start with ice cores. In Greenland and Antarctica, snow has fallen year after year for hundreds of thousands of years. Over time, that snow compresses into ice, trapping bubbles of ancient air and layers of dust, volcanic ash and sulfate. A large eruption can leave behind a sulfate spike, a chemical fingerprint of sulfuric acid aerosols once floating in the stratosphere. In theory, Toba should be easy to find. It was enormous. If it loaded the atmosphere with vast quantities of sulfur dioxide, ice cores might preserve a dramatic signal around 74,000 years ago. But deep-time ice is not a perfect archive. The farther back you go, the harder it becomes to date each layer precisely. Ice can thin, stretch, fold, or become disturbed as glaciers slowly flow under their own immense weight. A layer that appears to match Toba's age may be off by decades, centuries, or more. And even if sulfate is present, linking it to one specific volcano is difficult, unless researchers also find a matching chemical signature in microscopic volcanic glass. That is like trying to identify one explosion from the smoke stains it left on a wall tens of thousands of years later. Some ice core records suggest volcanic activity around the time of Toba, but they do not provide a simple, universally agreed answer saying, here is exactly how much sulfur Toba released, here is how long it remained in the sky, and here is the precise temperature drop that followed. Marine sediments raise similar problems. The ocean floor accumulates mud slowly, layer by layer. Within that mud are the remains of tiny organisms called foraminifera. Their shells preserve chemical clues about ancient ocean conditions, including temperature and ice volume. Other sediments record changes in wind-blown dust, rainfall runoff, plant matter, and the strength of monsoons. But oceans mix heat slowly. A volcanic winter lasting a few years may leave a much subtler mark in the deep ocean than a long-term climate shift lasting centuries. And the sediments themselves are rarely dated with the precision needed to isolate one eruption from every other climate fluctuation happening during the same period. That matters because Toba erupted during an already unstable chapter of the last ice age. Earth's climate was not sitting peacefully at one stable temperature, waiting for a volcano to disrupt it. Ice sheets were growing and shrinking, ocean circulation was shifting. Rain belts moved, monsoons changed strength. The Northern Hemisphere experienced abrupt cold events that could transform regional climates with shocking speed. So if a sediment record shows cooling near 74,000 years ago, scientists have to ask a difficult question. Was this Toba, or was it part of the climate system's own natural turbulence? Pollen records add another piece to the puzzle. Pollen grains are incredibly durable. Lakes, bogs, and caves can preserve them for tens of thousands of years. Different plants produce different pollen, so researchers can examine ancient layers and reconstruct changing landscapes. More grass pollen may suggest expanding grassland. More tree pollen may suggest wetter or warmer conditions. A sudden decline in vegetation can point toward drought, cooling, fire, or ecological disruption. But pollen does not come with a label explaining what caused the change. A forest can retreat because temperatures fell. It can retreat because rainfall weakened. It can retreat because humans burned vegetation. It can retreat because a lake basin changed or because the pollen blew in from somewhere else. And once again, matching a change in vegetation to a single year, or even a single decade, 74,000 years ago is extremely hard. Then there are the climate models. These are not guesses in the casual sense. They are mathematical simulations based on what scientists know about sunlight, atmospheric circulation, aerosols, clouds, oceans, and the chemistry of sulfur gases. Researchers can estimate a sulfur release, inject it into a simulated stratosphere, and watch what happens. How much sunlight gets reflected? How long do the aerosols remain aloft? Where does cooling become strongest? Do monsoons weaken? Do drought zones expand? Does sea ice grow? Does one cold season trigger ecological stress that lasts far beyond the aerosol cloud itself? The problem is that the answer depends heavily on the starting assumptions. We still do not know exactly how much sulfur dioxide Toba injected into the stratosphere. A giant eruption does not necessarily send all of its gas to the same altitude. The season matters, the latitude matters, the height of the eruption column matters. So does the size of the aerosol particles that formed afterward. This last point is crucial. More sulfur does not always mean proportionally more cooling. If aerosol particles become too large, they can clump together and fall out of the atmosphere faster. The stratosphere may not behave like a simple blanket that gets thicker forever. At extreme scales, the physics becomes more complicated. That is why early estimates of Toba's impact were often dramatic. Some studies suggested global cooling of several degrees Celsius, perhaps with far greater drops over certain continents. In the coldest scenarios, summers in some mid and high latitude regions could have become brutally short, with growing seasons collapsing and ecosystems taking years to recover. But newer modelling studies have often produced more limited results. They still find cooling. They still find disruption. But some suggest a global average temperature decline closer to around 1 degree Celsius, perhaps lasting a few years rather than a decade. That may sound modest. It is not necessarily modest. A global average is a strange number. It blends the Arctic with the tropics, oceans with land, wet regions with dry ones. A 1 degree global shift can conceal much sharper regional changes. One area might experience relatively mild cooling but severe drought because the monsoon weakens. Another might receive more rain but suffer from a shortened growing season. A coastal region with access to fish, shellfish, and mangroves might remain productive while an inland savanna loses game and water. A mountain valley could become unlivable, while a river corridor only a few hundred miles away becomes a refuge. For human beings, the average temperature of the planet was never the real question. The real question was local survival. Could your group still find water? Could children be fed through the lean season? Did the animals return? Did edible plants fruit? Could you move to another territory without fighting the people already there? That is why Toba's climatic impact cannot be translated into a clean death toll. The eruption was huge. The ash spread far. The potential for atmospheric cooling was real. But there is no ledger from 74,000 years ago listing the number of humans alive before the eruption and the number alive after it. And even if population declined in some regions, the cause might not have been Toba alone. Climate was already changing. Disease, competition, local drought, and ordinary bad luck could all push small hunter-gatherer groups toward collapse. Toba may have been a global shock, but a global shock does not produce one global outcome. It creates winners and losers, refuges and dead zones, groups that are trapped and groups that can move, landscapes that fail and landscapes that become lifelines. And that brings us to the number that turned Toba from a geological disaster into a story about human near extinction. 10,000 survivors, Where did that number actually come from? The number did not come from a mass grave. It did not come from ash layers containing the remains of 10,000 people. It did not come from an ancient census, because 74,000 years ago nobody was counting births, deaths, or how many families had vanished from a landscape. It came from our DNA. Every human alive today carries a genetic record of the past. Not a perfect record, not a diary with dates written in the margins. More like a library after a flood. Some pages are missing. Others are damaged, but enough survives for geneticists to reconstruct parts of the story. And one of the things they look for is genetic diversity. Imagine two populations. The first contains millions of people who have been interbreeding across a large area for a very long time. It will usually contain lots of genetic variation, different versions of genes, rare mutations, long family lines branching in many directions. Now imagine a population that crashes. Most family lines disappear. Many rare genetic variants vanish with them. The survivors reproduce, and over generations their descendants refill the landscape. The total number of people can become enormous again. But the genetic richness that existed before the crash may take a very long time to return. That is a bottleneck, and compared with many other animals, humans show surprisingly low genetic diversity. Two chimpanzees from the same forest can be more genetically different from each other than two humans chosen from opposite sides of the planet. That does not mean humans are genetically identical. Far from it. But it does suggest that somewhere in our deep past our lineage passed through periods when relatively few ancestors contributed genes to later generations. This is where the famous number enters the story. Genetic studies have often estimated that the ancestral population of Homo sapiens had an effective population size of roughly 10,000 individuals, sometimes lower, sometimes higher. The exact result changes depending on the method, the DNA being studied, and the assumptions built into the model. But notice the phrase effective population size. That does not mean exactly 10,000 human beings were walking around Earth, all at the same moment after Toba erupted. Effective population size is a technical genetic concept. It is the number of individuals in an idealized population that would produce the same patterns of genetic variation seen in the real one. And real populations are never ideal. Not everyone has the same number of children. Some people leave many descendants, others leave none. Groups may be isolated for generations, then reconnect. Men and women may contribute unequally to future generations. A population spread across Africa in small bands can contain far more actual people than its effective population size suggests. Think of it this way. A village might have 100 adults. But if only a small number of families have surviving children over many generations, then genetically, the village behaves more like a much smaller population. The census number tells you how many bodies are present. The effective population size tells you how many people are actually shaping the genetic future. Those are not the same thing. So when you hear that humanity fell to 10,000 survivors, the scientifically careful version is much less cinematic. Modern human DNA has often been interpreted as evidence that our ancestral population was relatively small, perhaps with an effective size on the order of 10,000 breeding individuals, during parts of our recent evolutionary past. That is a very different claim from saying a volcano reduced all humans on Earth to exactly 10,000 terrified people. How do researchers estimate something so ancient? They compare DNA sequences from living people across different populations. They count mutations. They look at how often genetic variants appear. They measure stretches of DNA inherited together, patterns shaped by population growth, isolation, migration, and collapse. Then they use mathematical models to run history backward. If two people carry similar DNA in one region of the genome, That section probably traces back to a shared ancestor. The farther back their lineages join, the more time mutations have had to accumulate. By studying millions of these tiny genetic histories, scientists can estimate when ancestral populations were larger, when they were smaller, and when groups may have expanded or separated. This is called coalescent analysis, and the name is perfect. Genetic lineages traced backward through time gradually coalesce. Separate branches merge into shared ancestors, but there is a catch. DNA can reveal that a population became small. It is much worse at telling you why. A bottleneck signal can be produced by drought, disease, migration, reproductive inequality, long-term population structure, or repeated local extinctions across a fragmented landscape. It can reflect a short, brutal crash, or a smaller population persisting for thousands of years. Different histories can leave similar genetic fingerprints. And dating the signal is difficult too. Mutations do not arrive like clockwork. Generation lengths change. Ancient populations were structured, not one giant randomly mating group. A genetic event estimated at around 70,000 years ago may carry a wide range of uncertainty. It may overlap Toba. It may begin before Toba. It may continue long after the ash settled. Early studies, especially studies of mitochondrial DNA, and later whole genome variation, helped create the impression that modern humans had passed through a severe bottleneck around the same broad period as the eruption. The timing was suggestive, the population estimate was dramatic, and Toba was already famous as one of the largest eruptions in the last few million years. Put those facts together and the story almost writes itself. A supereruption darkens the sky. The world cools. Plants fail. Animals die. Human groups collapse. Only 10,000 survive. It is a powerful narrative because it gives a vast geological event a human face. It turns a distant volcano into the moment our species nearly disappeared. It explains our low genetic diversity with one terrifying catastrophe. And it gives every person alive today a direct connection to a tiny band of survivors who supposedly endured the end of their world. But powerful is not the same as proven. The genetic evidence may tell us that our ancestors were few. Toba may have been a major environmental shock. The hard question is whether those two facts describe the same event. And genetics by itself cannot name the culprit, because DNA is not a crime scene. It can tell you that something happened. It can tell you the population was smaller than expected, that family lines disappeared, that genetic diversity was reduced. But it cannot point to a layer of volcanic ash and say, this was the weapon. This was the day. This was the culprit. Think about what happens when geneticists look backward through time. They are not watching individual people live and die. They are tracing surviving lineages, and surviving lineages are selective. They only show us the ancestors who left descendants alive today. If an entire population lived for thousands of years, raised children, made tools, migrated, and then eventually died out without leaving genetic descendants in later populations, much of its story may simply vanish from the DNA record. Their lives were real, their numbers mattered. But genetically, they can become almost invisible. That makes a bottleneck less like a photograph of one disaster and more like a shadow cast across a very long stretch of time. A population might decline gradually over 20,000 years as rainfall patterns shift and grasslands retreat. Small groups might become isolated in separate refuges. Some groups may survive while others disappear. Later, a few successful populations expand and absorb or replace their neighbours. When geneticists look back from the present, that complicated history can resemble a single population crash. And that is before we even get to the possible causes. Drought could do it. Not necessarily one dramatic drought, but repeated dry periods that shrink lakes, weaken river systems, reduce edible plants, and scatter animal herds. Human populations depend on food webs. When plants decline, herbivores decline. When herbivores decline, hunters have fewer options. A few bad seasons can be survived. A few thousand bad years can reshape an entire species. Disease could do it too. We tend to imagine ancient humans as too scattered for epidemics. And it is true that small mobile bands probably could not sustain the same explosive outbreaks seen in cities. But disease does not need to wipe out everyone at once to affect population size. A new pathogen moving through connected groups, perhaps carried by animals, perhaps spreading along marriage or exchange networks, could lower survival rates generation after generation. Fewer children reaching adulthood, more mothers dying in childbirth, smaller groups becoming vulnerable to every other threat. Migration can create the same genetic illusion. Imagine a population spread across Africa. One group remains in the south, another moves east, a third enters a new region and grows rapidly because it finds better resources. Thousands of years later, descendants of that expanding group may contribute far more DNA to living people than the groups that stayed behind. The genetic record would then be dominated by the winners. That does not necessarily mean everyone else died in a single catastrophe. It may mean their descendants were gradually absorbed, displaced, or simply outnumbered. In genetics, expansion can erase evidence almost as effectively as extinction. This is one of the hardest parts of the mystery. Later success can blur earlier suffering. When a population expands rapidly, it carries only a sample of the genetic diversity that existed before. Rare variants from older populations can disappear. New mutations accumulate. Migrations mix lineages that were once separate. Over tens of thousands of years, the original signal becomes distorted, like footprints on a beach after wave upon wave has passed over them. So even if Toba did cause severe hardship in some regions, later population growth could make its specific genetic impact difficult to isolate. And the reverse is also true. A bottleneck signal that appears to overlap the time of Toba may have been caused mostly by events that began before the eruption, continued after it, or had nothing to do with volcanoes at all. This is why researchers disagree. Some studies have found evidence consistent with a relatively small ancestral Homo sapiens population during broad periods in the late Pleistocene, including around the time of Toba. Other studies suggest the reduction was not as sudden, not as extreme, or not precisely dated enough to connect confidently to one eruption. Some models infer a long period of low effective population size rather than a sharp crash. Others find evidence that African populations were deeply structured. Small groups separated across huge distances, sometimes exchanging genes, sometimes remaining isolated for thousands of years. Under those conditions, a low effective population size may partly reflect the way populations were organized, not a moment when all humanity nearly vanished. That distinction matters. Imagine 100 small camps spread across a continent. Each camp has only a few dozen people. Most people marry within or near their own group. Contact between distant camps is rare. Genetically, the whole population does not behave like one large, freely mixing population of several thousand people. It behaves more like many small populations connected by thin, fragile threads. Now add climate change. One region dries out, another becomes more favourable. A few camps vanish, others grow, some migrants move into empty territory. None of this requires a single global disaster, but over time, it can produce exactly the kind of reduced diversity that researchers call a bottleneck. And then there is the problem of dates. 74,000 years sounds precise, because the eruption can be dated with remarkable accuracy. The volcanic ash is a physical event. It happened. It left a layer in the ground. Genetic dates are different. They depend on mutation rates, estimates of generation time, assumptions about migration, and models of ancient population structure. Change those assumptions and the inferred timing can shift by thousands, sometimes tens of thousands of years. A genetic decline that broadly overlaps Toba is interesting. It is not the same as proving that the decline began the year the volcano erupted. This does not mean genetics is useless, far from it. Genetics has transformed our understanding of human origins. It has revealed ancient migrations, interbreeding with Neanderthals and Denisovans, population expansions, and the deep connections between people living on different continents. It tells us that our species has survived periods of small population size and immense environmental instability. But it cannot, on its own, reconstruct the exact chain of events. To blame Toba, we need more than a reduced genetic signal and a famous eruption occurring in the same broad window of time. We need evidence that people in affected regions actually suffered a sharp collapse. We need archaeology. We need climate records. We need sites showing what happened before the ash arrived, while it was falling and after the world began to recover. And one of the most important places to look is India. Because there, in landscapes touched directly by Toba's ash, archaeologists found something that complicates the disaster story even further: stone tools below the ash and stone tools above it. In southern India, in what is now Andhra Pradesh, there is a cluster of archaeological sites called Jwalapuram. At first glance, it is not the kind of place you would expect to settle one of the biggest arguments in human prehistory. No giant skeletons, no buried city, no dramatic monument left by the survivors. Just stone flakes, blades, points and scrapers, lying in layers of ancient sediment. But one of those layers contains Toba ash. This is the crucial detail. The youngest Toba tuff, the ash from the eruption 74,000 years ago, spread across huge areas of India. At Jwalapuram, archaeologists found it preserved as a distinct volcanic deposit, a physical timestamp in the ground. Beneath it were stone tools made before the eruption, and above it were more stone tools made after the ash had fallen. That sounds simple, but it is potentially devastating to the most extreme version of the Toba catastrophe theory. If the eruption had turned India into an uninhabitable wasteland and wiped out every human population across the region, then what are stone tools doing above the ash? Someone was still there, or at least someone returned soon enough that the archaeological sequence does not show the kind of long, empty gap we might expect after total regional collapse. The tools below the ash belong broadly to what archaeologists call a Middle Paleolithic technology. These were not the old heavy hand axes that had dominated much of earlier human prehistory. They were smaller, more flexible tools made by carefully striking flakes from prepared pieces of stone. The flakes could be sharpened into cutting edges, scraping tools or points. This was a technology suited to mobile people who needed useful equipment without carrying massive chunks of rock across the landscape. And above the Toba ash, archaeologists found tools with strikingly similar characteristics. Not an abandoned landscape, not a clear technological reset. Not obvious evidence that every local tradition vanished and was replaced thousands of years later by newcomers with an entirely different toolkit. Instead, there appears to be continuity. Now, continuity does not mean life was easy. Imagine the ashfall itself, fine volcanic dust settling over rivers, grasslands, campsites, and food sources. Animals fleeing or dying in some areas, water becoming contaminated, plants damaged, people forced to move, change where they hunted, alter what they ate, and perhaps abandon familiar territories. A volcanic eruption on Toba's scale could still have been terrifying, disruptive and deadly without erasing every human group in its path. That is the point Jwalapuram forces us to confront. Survival is not the same thing as no impact. A population can survive a catastrophe while losing people, territory, children, knowledge, and access to resources. Groups may scatter. Some may die out entirely. Others may endure because they happen to be near a reliable water source, because they could exploit a wider range of foods, or because their social networks brought help from beyond the worst affected zone. The archaeological record at Jawalapuram does not tell us that Toba was harmless. It tells us the simple version of the story may be wrong. The simple version says, volcano erupts, ash falls, humans disappear. But the ground in India seems to say something more complicated. Tools before the ash, tools after the ash. Human activity continuing across one of the greatest volcanic events of the last several 100,000 years. And then the mystery gets even deeper. Who made those tools? For years, the Jawalapuram evidence has been discussed as possible proof that Homo sapiens had reached India before Toba erupted. If modern humans were already living there 74,000 years ago, and if their tool-making continued afterward, then they may have survived the ashfall directly. That would challenge the idea that Toba created a global bottleneck so severe that only a tiny remnant of our species endured somewhere else. It would also push part of the story of human migration out of Africa earlier than some older models allowed. But archaeology has a frustrating rule. Stone tools do not come with name tags. A tool can reveal how it was made. It can suggest planning, skill, and cultural tradition. It can sometimes show whether its maker was hunting, butchering animals, scraping hides, or processing plants. But unless a fossil is found in a secure association with those artifacts, identifying the toolmaker is difficult. And at Jawalapuram, there are no hominin fossils preserved beside the tools that can settle the question. The makers may have been Homo sapiens. They may have been another human population living in South Asia. They may even represent a population whose identity we cannot yet name, because the fossil record from this period is so incomplete. This matters because the same stone technology can sometimes be used by different human groups. Neanderthals made Middle Paleolithic tools in Europe and Western Asia. Early modern humans made related technologies in Africa and the Near East. Across prehistoric Asia, we still do not fully understand how many hominin populations existed, where they lived, or how often they encountered one another. So Jawalapuram does not provide a neat answer. It provides a problem for anyone claiming certainty. If Homo sapiens made the tools both below and above the ash, then at least one population of our species appears to have endured Toba in India. That would make a single species-wide near extinction harder to defend. If another hominin made them, the site still matters enormously. It would show that Toba did not produce total regional collapse among all human populations. Some people, somewhere in southern India, retained the ability to find stone, make tools, and survive in the aftermath. And even that conclusion needs care. An ash layer can represent a sudden event, but the sediments above and below it may cover years, centuries, or longer. Similar-looking tools do not prove that the exact same family, band, or even population remained continuously in one place through the eruption. A group could have survived nearby and moved in later. Newcomers could have adopted a local tool-making tradition. Archaeology can show continuity in behaviour without proving uninterrupted continuity of every individual community. But that uncertainty does not rescue the extinction scenario, because a world truly shattered beyond recovery should leave a clearer silence. Long gaps with no evidence of occupation, abrupt disappearance of technologies, landscapes abandoned for thousands of years, signs that human activity had to begin again from scratch after the ash settled. At Jawalapuram, that is not the pattern archaeologists found. Instead, the evidence suggests resilience, not necessarily comfort, not necessarily growth, resilience. And that changes the question. Maybe Toba did not reduce humanity to one tiny isolated pocket of survivors. Maybe its effects varied dramatically from place to place. Some regions may have suffered severe disruption, others may have remained habitable. Some groups may have collapsed, while neighbouring populations, separated by only a few hundred miles, found ways to endure. India, lying beneath the shadow of Toba's ash, may preserve one of the clearest warnings against turning a real disaster into an overly simple story. The eruption was enormous, the human response may have been uneven. And to understand what that uneven survival looked like, we have to move beyond the question of whether humanity lived or died. We have to ask where people could survive, why some places became refuges, and why the same catastrophe might have meant disaster in one landscape and endurance in another. That is the real middle of the mystery. Not, did Toba kill everyone? But who was close enough to suffer the worst effects? Who had somewhere else to go? And which landscapes still had enough food, water, and shelter to keep a small human population alive? Because disasters are never experienced evenly. Near Lake Toba itself, the situation may have been almost unimaginable. The eruption unleashed vast quantities of ash, rock, and volcanic gases. Areas around the volcano would have faced the direct violence of the blast, then darkness, ashfall, poisoned water, damaged forests, and the collapse of local animal populations. For people living close to the eruption, familiar territory could have become unrecognizable in days. A river they relied on might be choked with sediment. A forest full of edible plants and game might be buried. Fine ash could contaminate waterholes, damage lungs, and make food gathering far harder. Even groups that escaped the immediate disaster may have been forced to abandon territories their families had known for generations. And when people are pushed out of their land, survival becomes dangerous in a new way. They have to enter someone else's territory. They have to compete for already limited food. They have to find safe campsites without knowing the seasonal patterns, the water sources, the dangerous animals, or the people who may already be living there. A catastrophe does not have to kill every individual directly. It can trigger starvation, conflict, displacement, and a slow breakdown of the systems that made life possible. But move farther away from Toba and the picture changes. India was blanketed by ash in some regions, but the thickness of that ash varied enormously. Southern India may have endured serious disruption, yet the archaeological record suggests it was not transformed into a lifeless, empty zone. People may have shifted their diets, moved toward rivers, changed hunting grounds, or relied more heavily on small animals, fish, shellfish, roots, seeds, and other foods that could survive when large game became scarce. That kind of flexibility matters. A group dependent on one herd species, one seasonal grassland, or one water source is vulnerable. A group that knows how to exploit 10 different food sources has options. They can eat shellfish when hunting fails. They can trap small animals when large animals disappear. They can dig for roots, collect seeds, gather insects, fish tidal pools, or follow rivers toward wetlands that still support life. And some of the most important refuges may have been coastlines. Coasts are not easy places to live. Storms can be deadly. Fresh water can be difficult to find. Tides change the landscape twice a day. But coastlines can also provide an unusually reliable buffet for people with the knowledge to use them. Shellfish do not run away. Fish can be trapped in shallow pools. Seabirds, eggs, crabs, edible plants, and stranded marine animals can all supplement a diet when inland ecosystems are failing. During a volcanic crisis, that reliability could mean the difference between a shrinking population and a vanished one. Caves may have offered another advantage. not magical protection. A cave cannot feed you. It cannot stop a regional drought or replace a lost hunting ground. But it can provide shelter from ashfall, wind, cold nights and rain. It can preserve fire. It can become a base from which people range outward, searching for food and returning to a place they know is safe. Wetlands, too, may have been lifelines. Even when dry landscapes become harsher, wetlands can concentrate water, plants, birds, fish and grazing animals into a smaller area. They attract life, and where life gathers, humans can survive. A marsh, lake edge, river floodplain or spring-fed valley might have supported people when the surrounding countryside could not. This is why it is so difficult to talk about Toba as if one climate effect applied equally across the whole planet. Africa was thousands of miles from the eruption. It may have experienced climatic stress related to the event, especially if volcanic aerosols contributed to cooler or drier conditions. But the evidence does not support a simple picture of the entire continent becoming instantly uninhabitable. Africa is not one environment. It contains deserts, savannas, highlands, forests, lakes, river systems, and long coastlines. A drought that devastates one region can leave another relatively stable. A cooling event that disrupts one food web may create opportunities somewhere else. Southeast Asia presents the same problem for the simple extinction story. It was closer to Toba, and some areas may have been hit hard. But it was also a vast region of islands, forests, rivers, coastal plains, and changing sea levels. People did not need every place to remain livable. They only needed some places to remain livable long enough for populations to recover. And they needed to move. Mobility was probably one of the greatest survival technologies humans possessed. Long before farming, cities, or written records, people could respond to environmental change by leaving. They could follow animals, they could move toward water. They could return to places their ancestors remembered as reliable during bad years. A small group carrying stone tools, fire knowledge, and social ties could abandon a failing landscape far more easily than a settled agricultural society. But mobility works best when people are not alone. This is where social networks become crucial. Small human groups may have maintained contact with neighbouring bands through kinship, exchange, marriage, and seasonal meetings. We cannot map those networks in detail 74,000 years later, but hunter-gatherer societies in many times and places have depended on them. When one group faces hunger, relatives elsewhere may offer food, shelter, mates, information, or access to territory. A network can absorb shocks that would destroy an isolated band. If one camp loses its water source, it may join another. If a hunting ground fails, people may know of a distant wetland, a coastal shellfish bed, or a sheltered valley where conditions are better. Knowledge itself becomes a survival resource, not just where food is today, but where it was during the last drought, where stone can be found, which plants remain edible after ashfall, and which roots avoid the worst damage. And if you want to explore more mysteries where the evidence is real, but the final answer remains frustratingly out of reach, you can get our book about the 12 unexplained mysteries on our website. The link is in the description. Toba may have destroyed communities. It may have forced others to migrate. It may have reduced populations in some regions so severely that their genetic traces disappeared forever. A catastrophe on that scale does not need to erase a species globally to reshape its future. Think about a fire sweeping through a forest. Some areas burn to bare ground. Some trees are killed but remain standing. Some valleys escape because of wind, moisture, or sheer geography. And in isolated pockets, seeds, insects, birds, and small animals survive. Later, the forest grows back from those fragments. Humanity may have endured Toba in much the same way. not as one unified population standing against one global disaster, but as scattered groups facing radically different versions of the same event. Some may have died in the ash zone, some may have been displaced into unfamiliar lands, some may have survived in caves, along rivers, beside wetlands or on coasts where the food supply was more dependable. Some may never have experienced the disaster as a sudden apocalypse at all, only as years of strange weather, changing animal movements, and harder choices. That reframes the entire story. The question is not whether Toba nearly erased every human being alive. The better question is whether it created a patchwork of collapse and survival, pushing some populations to extinction, while forcing others to adapt, relocate, and connect more tightly than before. And if that is what happened, then the genetic story becomes even more complicated, because a reduced population is not the same thing as a single tiny group of survivors. And that brings us to Africa. If Toba caused a global crisis, Africa is where we should expect to see the consequences most clearly. This was the continent where Homo sapiens had evolved. It contained many of the populations whose descendants would later spread into the rest of the world. If the eruption drove humanity down to a tiny number, then somewhere in Africa people had to survive the worst years. But Africa does not give us one simple answer. It gives us a mosaic. Around 74,000 years ago, the continent was already changing. The late Pleistocene was a period of unstable climate, with rainfall patterns shifting over thousands of years, lakes rising and falling, deserts expanding and retreating, and grasslands changing into woodland or dry scrub, depending on the region. Long before Toba erupted, African communities were living in a world where water could disappear, animal migrations could shift, and familiar food sources could become unreliable. The evidence comes from lake sediments, cave deposits, pollen grains, ancient shorelines, and chemical signatures trapped in mud and rock. These records can tell us whether a lake was deep or shallow, whether plants were growing in wetter or drier conditions, whether erosion increased after vegetation vanished. But they do not give us a continent-wide weather report for a single year. They are more like damaged pages from a very old diary. One lake basin may preserve evidence of drought, another may show water still present. A coastal cave may reveal humans continuing to use shellfish and small animals. An inland region may leave almost no record at all, and because these records often have dating uncertainties of centuries or even thousands of years, tying a specific environmental shift directly to the Toba eruption is incredibly difficult. Still, the broad picture is clear enough. Africa was not stable. In East Africa, lake levels changed dramatically during the late Pleistocene. Some basins expanded during wetter phases, creating wide shorelines, wetlands, and rich feeding grounds for animals and people. During drier phases, those same lakes could shrink, break into smaller water bodies, or leave exposed plains where fish, birds, reeds, and grazing animals had once gathered. For a human group living near a lake, that could be devastating. A shallow lake means less fish. Fewer wetlands mean fewer birds and edible plants. Grazing animals may move away. Water becomes concentrated into fewer places, and suddenly every surviving spring or shoreline becomes territory worth fighting over. But a shrinking lake could also create opportunities. As water retreated, it might expose new grasslands. Animals could concentrate around the remaining water. Fish trapped in shallow pools might become easier to catch. Humans are not passive victims of environmental change. They can shift camps, change diets, alter hunting strategies, and exploit resources that become available only because the landscape is changing. That is one of the biggest problems with the idea of a single African collapse. A dry period in one place may be a disaster. In another, it may reorganize the landscape without making it unlivable. and Toba was only one possible influence among many. Volcanic aerosols may have reduced sunlight and disrupted rainfall for a period after the eruption. That is physically plausible, but African climate was also shaped by forces operating on much larger timescales. Changes in Earth's orbit altered the strength of seasonal sunlight. The position of tropical rain belts shifted north and south. The Indian Ocean and Atlantic Ocean influenced moisture moving onto the continent. Ice sheets far to the north affected global circulation. Monsoon systems strengthened and weakened. Ocean temperatures changed. Africa was connected to the whole planet. A volcanic winter, if it occurred, would have entered an environmental system already in motion. It might have intensified drought in one region, weakened rains in another, or produced effects that varied from season to season. Some areas may have cooled, others may have received less rain without dramatic cooling. Still others may have been buffered by nearby oceans, mountains, groundwater, or permanent rivers. This is why saying Africa suffered after Toba is true only in the broadest possible sense. Which Africa? The dry interior of southern Africa is not the Rift Valley. The Rift Valley is not the Ethiopian highlands. The Ethiopian highlands are not the Congo Basin. The Congo Basin is not the North African coast. Each region had different rainfall patterns, different plants, different animals, different routes of movement, and different possibilities for survival. And the people living there were not one single population either. They were scattered hunter-gatherer groups, probably connected unevenly through kinship, exchange, marriage, and movement across generations. Some groups may have lived near lakes and rivers. Others may have followed seasonal herds across grasslands. Some may have occupied coastal zones. Others may have moved through woodland corridors, highland valleys, or semi-arid scrub. A crisis would not hit all of them equally. The most likely refuges were not necessarily places untouched by hardship. They were places where hardship remained survivable. Coastal southern Africa is one candidate. Marine foods could provide a buffer when inland hunting became less reliable. Shellfish, fish, seabirds, eggs, seals, edible plants, and stranded animals offered resources that did not depend entirely on seasonal rainfall. A coastline could not solve every problem, especially if fresh water was scarce, but it could support people through bad years. Lake margins and river corridors may have been equally important. Water draws animals. It supports plants. It creates reeds for shelter and fuel, fish for food, and predictable places where people can return after moving through harsher country. Even a reduced lake can remain a lifeline if it still holds water when everything around it is drying out. Highlands may have offered another kind of refuge. Elevation can create cooler temperatures, local rainfall, springs, and ecological diversity within a relatively small area. Forested zones may also have sheltered communities in some regions, though forests brought their own challenges: dense vegetation, dangerous animals, and resources that required specialized knowledge. There was no single safe haven. There were probably many temporary havens, each supporting small populations in different ways. And that may be the real lesson of Africa during the Toba era. Humanity did not survive because one perfect refuge protected one chosen group. Survival may have depended on a network of imperfect landscapes, each holding on just long enough for people to adapt, move, and remain connected. The eruption may have made life harder. Climate shifts may have pushed some groups past the breaking point, but across a continent this large and varied, total collapse was never the only possible outcome. The survivors may not have been hidden in one place. They may have been everywhere. The landscape still gave them one more chance. One more chance was not enough by itself. A spring can keep a group alive for a season. A rich shellfish bed can carry them through a bad month. A herd passing through a valley can mean meat, fat, hides, and bone tools when nothing else is available. But what happens when the spring fails? When the shellfish beds are too far away? When the herd changes its migration route, or another group reaches the water first? For small hunter-gatherer communities, survival depended on having somewhere else to turn. And that is where human networks may have mattered more than any single refuge. Picture a group of maybe 20 or 30 people living near a river corridor. They know the local animals, the edible roots, the places where stone can be found, the timing of the rains. But their territory is only one small piece of a much larger world. Beyond the next ridge, perhaps another group lives near a lake. Farther away, others know the coast. Others know a mountain pass, a seasonal wetland, a grove of fruit trees, or a source of high-quality stone for making blades and spear points. In good years, these groups might meet only occasionally. A few families travelling, a shared hunt, a marriage arrangement, the exchange of stone, shells, pigments, animal skins, or information. In bad years, those connections could become the difference between a local disaster and extinction. If drought destroyed the food supply in one territory, people could move toward relatives or allies elsewhere. If one group had lost hunters, another group might absorb survivors. If a community knew how to catch fish in shallow water, preserve meat, find underground tubers, or make tools from a different kind of stone, that knowledge could travel far beyond the people who first developed it. This is a simple idea, but it is incredibly powerful. No small group can know everything. No single landscape provides every resource every year. But a network can spread risk. Anthropologists studying recent and historical hunter-gatherer societies have seen versions of this strategy again and again. People maintain relationships beyond their immediate camp. They exchange gifts, they visit kin, they arrange marriages with distant groups. They share food when times are hard, not because everyone is always generous, but because the favour may one day need to be returned. You help another group survive a failed season because next year, the failed season may be yours. 74,000 years ago, these networks would not have looked like trade routes on a map. There were no cities, no caravans, no warehouses full of grain. The connections may have been fragile, seasonal, and stretched across generations. A shell bead passed from one group to another, a distinctive stone tool style appearing far from its source. A person marrying into a distant camp and carrying memories of wells, trails, food plants, and family obligations. But that kind of connection creates resilience. It also protects genetic diversity. A tiny isolated group faces a dangerous problem. If everyone is closely related, harmful genetic variants can become more common. If there are too few potential partners, birth rates may fall and social tensions may rise. Exchanging mates between groups is not just a cultural practice. It is a biological survival strategy. It keeps populations connected, reduces inbreeding, and allows a scattered human population to remain part of a larger whole. This may be one reason the image of exactly 10,000 people huddled in one last refuge is probably misleading. Even if human numbers dropped sharply at some point in the distant past, survival was likely distributed. Small communities separated by long distances, each facing different conditions, each losing people and gaining people over time. Some groups disappearing completely, others surviving. Others receiving migrants, others sending them out. Not one lifeboat, more like a chain of small boats, sometimes losing sight of each other, but not entirely cut loose. And the people in those boats were flexible. That may have been their greatest advantage. If large game became scarce, they could hunt smaller animals. If grasslands dried out, they could search river margins, woodland edges, or coastal zones. If seasonal plants failed, they could dig for roots and tubers, collect nuts, gather seeds, strip bark, harvest insects, trap reptiles, or exploit birds and their eggs. None of these foods sounds dramatic. That is exactly the point. Survival is often built from ordinary things. A coastline, for example, could provide shellfish that were slow to escape and relatively predictable at low tide. Fish could be trapped in pools, speared in shallows, or gathered when changing conditions concentrated them in smaller waterways. Seabirds, seals, stranded marine animals, and coastal plants added more options. Inland, hunters could follow antelope, zebra, or smaller prey. Gatherers could rely on plant knowledge accumulated over countless seasons. Different environments demanded different skills, and human culture allowed those skills to spread faster than genes ever could. A child did not have to rediscover which plants were poisonous. They could be taught. A young hunter did not have to invent every technique from scratch. They could learn from older hunters. A group arriving in unfamiliar territory could gain access to local knowledge through kinship, exchange, and cooperation. That is cultural flexibility, the ability to change behavior before evolution has time to change the body. And it rarely leaves behind the kind of evidence people expect. There may be no monument saying, this community survived the Toba eruption through mutual aid, no written record of a marriage alliance that linked two distant valleys, no map of seasonal movements between coast, grassland, and river. Instead, the clues are subtle. A stone tool made from rock found many kilometers away. Shells carried inland. Similar tool-making methods appearing across separate regions. Repeated occupation of a cave or shoreline through changing environmental conditions. A shift in diet visible in animal bones, shell deposits, or microscopic traces on tools. These are not spectacular remains, but they may record something far more important than spectacle. They may record people refusing to be trapped by one place, one food source, one strategy, or one another. And if these human networks helped communities survive environmental shocks, they may also have shaped the next great question in the Toba mystery. Did the eruption merely make life harder for Homo sapiens? Or did it delay the moment when some of those connected African populations would finally begin moving out into the wider world? That question takes us beyond the eruption itself, beyond ash layers and temperature records, into the biggest journey in human history. The expansion of Homo sapiens out of Africa. At some point, small groups of our species crossed into Southwest Asia. Their descendants eventually reached every habitable continent, from the frozen north of Europe to the islands of the Pacific, from Siberia to the southern tip of South America. But the route out of Africa was not one single march, and it probably did not happen once. For a long time, the story seemed simple. Modern humans evolved in Africa, remained there until around 60,000 or 70,000 years ago. Then a small population left and rapidly spread across Eurasia. That later expansion is still enormously important. Most genetic ancestry in living people outside Africa traces back to populations connected to that movement. But archaeology has made the picture messier. Human fossils in the Levant suggest that Homo sapiens reached the eastern Mediterranean much earlier, perhaps more than 100,000 years ago. Evidence from Arabia has raised the possibility that people moved into parts of the peninsula during wetter periods, when deserts became grasslands and dry basins filled with lakes. There may have been repeated attempts, groups moving out, groups disappearing, groups returning, populations expanding during favourable climate windows, then contracting when the landscape turned hostile again. So by the time Toba erupted 74,000 years ago, Homo sapiens may already have been testing the edges of Africa for tens of thousands of years. That does not mean they had completed the global migration. Far from it. The major later expansion, the one that left the deepest genetic mark in people living outside Africa today, happened around the same broad period as Toba or somewhat afterward, depending on which evidence you emphasize. And that overlap has made the volcano impossible to ignore. Could Toba have delayed the migration? It is possible. But possible is not the same as proven. Imagine the routes available to early humans. To the north there was the Sinai and the Levant, a corridor between Africa and Western Asia. To the east there was the Bab el-Mandeb Strait, the narrow water crossing between the Horn of Africa and Arabia. Beyond it lay coasts, deserts, seasonal rivers, and mountain passes. These were not permanent highways. They opened and closed with climate. When rainfall increased, grasslands expanded, lakes appeared. Herd animals moved into new territories. Fresh water became available across landscapes that are now nearly barren. A small human population could follow those opportunities outward. But when drought returned, the same corridor could become a trap. Water sources vanished. Vegetation shrank. Animal populations scattered. A journey that had been possible for one generation might become impossible for the next. If Toba caused even a short-lived disruption to rainfall patterns, vegetation, or food webs, it could have made those already fragile routes more difficult. Not necessarily by burying travellers beneath ash. In much of Africa and Arabia, the more important effect may have been environmental uncertainty. Fewer reliable water sources, less predictable hunting, failed seasonal foods, more pressure on the small groups already living at the margins. And migration is not something desperate people do automatically. Sometimes hardship pushes people to move, but extreme hardship can do the opposite. A population struggling to feed children, maintain fire, replace broken tools, and survive the next dry season may not have the numbers or security to send groups into unknown territory. Expansion requires surplus. It requires enough people that some can leave without collapsing the community behind them. It requires knowledge of routes, access to water, social connections ahead, and enough stability to take risks. Toba may have interrupted some of those conditions. It may have closed corridors that were already opening and closing with the climate. But the evidence cannot yet tell us that the eruption was the reason a particular migration failed, paused, or turned back. South Asia is central to this mystery. For years it was often described as one of the great disaster zones of the Toba eruption. Ash from the volcano spread across the Indian subcontinent. In some places the deposit is unmistakable, a geological timestamp separating the world before the eruption from the world after. But beneath and above that ash, archaeologists have found stone tools. That does not automatically tell us exactly who made them. It does not prove that modern humans were already living across India. Some may have been made by other human groups. The dates are debated, the tool traditions can be difficult to assign to a specific species, and ancient landscapes rarely preserve a complete record. Still, the larger point is hard to avoid. South Asia was not empty. It was a crossroads. A vast region between Africa, Arabia, Southeast Asia, and the interior of Eurasia. People may have moved through it, lived there for generations, exchanged knowledge there, or encountered other human populations there. Even if Toba disrupted local environments, it did not necessarily erase every community or seal every route. In fact, the persistence of stone tool traditions across the ash suggests a more complicated reality. Some populations may have survived locally, others may have shifted into refuges along rivers, coasts, wetlands, or forest edges. Some routes may have become harder while others became more important. That is why the migration debate must be separated from the volcano debate. We can ask when Homo sapiens first left Africa. We can ask when the ancestors of most living non-Africans began their expansion. We can ask whether early movements reached Arabia, the Levant, India, or farther east before 74,000 years ago. Those are timing questions. Then we can ask whether Toba directly caused a delay. That is a causation question, and it is much harder. The eruption may have been one obstacle among many. Drought cycles, changing sea levels, shifting monsoons, competition for territory, and the simple danger of entering landscapes already occupied by other humans. Because when Homo sapiens moved beyond Africa, they were not entering an empty world. They were walking into a continent-sized meeting ground filled with other survivors. Those other survivors had names. In Europe and Western Asia, Neanderthals. Across parts of Asia, the population we now call Denisovans. And possibly other human groups we can barely identify at all. Because fossils are rare, DNA almost never survives, and stone tools do not come with name tags. This is one of the strangest facts about the world after Toba. 74,000 years ago, Homo sapiens was not the only kind of human trying to survive a dangerous planet. There were multiple human lineages, each with its own history, its own territories, its own ways of finding food, making tools, raising children, and enduring climate change. And Toba did not strike all of them equally. Neanderthals were living mainly across Europe and Western Asia, in landscapes shaped by cold, seasonal weather, shifting forests, open grasslands, and the advancing and retreating ice sheets of the last ice age. Their world was already difficult. A harsh winter did not need a supereruption to be deadly. Herds could move, plant foods could fail, snow and ice could cut off familiar routes. A small hunting group could lose a few adults and suddenly face a crisis. But Neanderthals were not helpless victims wandering through a frozen wilderness. They had survived for hundreds of thousands of years before Toba. They knew their territories in extraordinary detail. They hunted large animals, they used fire, they made sophisticated stone tools. They could process hides, work wood, and organize life around the seasonal movements of prey. In some places they returned to the same sites again and again, generation after generation. If Toba altered climate patterns in Western Eurasia, Neanderthals would have faced those changes through the filter of an environment they already understood. The problem is we do not yet have a clear archaeological signal saying, here is the moment Toba devastated Neanderthal populations. There is no continent-wide Neanderthal disappearance line neatly dated to 74,000 years ago. No unmistakable collapse in every tool tradition. No single ash-covered site showing that one eruption decided their fate. That does not mean the eruption had no effect. It means the effect, if there was one, may have been regional, uneven, and tangled up with everything else happening in the Ice Age world. A colder decade in one place could reduce vegetation and push grazing animals into new territory. That could force human groups to travel farther, compete more intensely, or abandon familiar hunting grounds. But another region protected by local geography, rivers, forests, or coastal resources might remain habitable enough to become a refuge. This is the key. There was no single human world for Toba to destroy. There were many worlds. A group living near a dependable river faced different risks from a group hunting reindeer on an exposed plain. A population on a coast could turn to shellfish, fish, seabirds and marine mammals when inland resources became unreliable. A group in a mountain valley might be insulated from some changes but trapped by others. Ashfall, temperature, rainfall, plant recovery, animal movement, and access to water all varied from place to place. And then there are the Denisovans. We know they existed because of a few remarkable fossils, and more importantly, because they left genetic traces in living people. Their DNA survives today in populations across Asia and Oceania. One famous Denisovan genetic contribution helps modern Tibetans cope with low oxygen at high altitude. That means ancient encounters between different human groups left behind survival advantages that are still useful tens of thousands of years later. But Denisovans remain deeply mysterious. We do not know exactly how many distinct Denisovan populations existed. We do not know their full geographic range. They may have occupied huge stretches of Asia from high mountains to tropical forests. Genetic evidence suggests they were not one small uniform population. They were probably diverse, separated by distance and ecology, adapting to very different environments. That makes it especially hard to say what Toba did to them. Some Denisovan groups may have lived far from the heaviest ashfall. Others may have occupied regions where changing monsoons affected forests, rivers, and food supplies. Some may have moved, some may have contracted into refuges. Some may have been absorbed into neighbouring populations. And some may have disappeared without leaving enough fossils for us to ever know their names. The archaeological record is not a complete map of survival. It is a handful of surviving pages from a book mostly destroyed. But later events reveal something important. When Homo sapiens expanded farther into Eurasia, our ancestors encountered these other humans. They did not only compete, they sometimes had children together. Most people with ancestry outside Africa carry small amounts of Neanderthal DNA. Some populations in East Asia, Southeast Asia, and Oceania also carry Denisovan ancestry. These genes are evidence of meetings, not abstract population arrows on a map, but real encounters between communities that had survived different climates, different migrations, and perhaps different consequences of Toba itself. In some cases, the genes that pass between groups may have helped people survive. Neanderthal DNA has been linked to immune function and adaptations to Eurasian environments. Denisovan DNA contributed to high-altitude adaptation in Tibetans. Ancient humans were not isolated branches cleanly replacing one another. They were populations meeting, mixing, competing, cooperating, and exchanging genes across a changing world. So Toba was not a reset button that produced one simple winner. It was one enormous disturbance inside a much larger story of climate instability, migration, adaptation, and contact between human lineages. Some groups may have suffered, some may have found refuge. Some may have recovered quickly, others may have been weakened by pressures that began long before the eruption and continued long after the ash settled. And that complexity matters, because it challenges the most dramatic version of the Toba story. If a supereruption truly caused a near-global human collapse, we should expect more than a powerful narrative. We should expect evidence, and this is where the argument becomes a real scientific fight. On one side are researchers who look at the scale of Toba and see a disaster almost too large for small human populations to absorb. The youngest Toba Tuff eruption was one of the biggest volcanic events of the last few million years. It blasted enormous quantities of ash into the atmosphere. It released sulfur gases high into the stratosphere, where they could form reflective aerosols and reduce the sunlight reaching Earth's surface. For a modern global civilization, that would be a crisis. For hunter-gatherers living in small scattered groups with no stored grain, no cities, no long-distance supply chains, and no way to predict what was coming, it could have been catastrophic. The strongest version of the catastrophe theory does not require every human being to have been buried in ash. In fact, most would not have been. The real danger was what came afterward. Cooler temperatures, weaker monsoons, shorter growing seasons, drought in already dry regions, plants failing to recover, herds moving, shrinking or disappearing, water sources becoming unreliable. A few bad years can be devastating when a group depends on daily access to food. A decade of ecological disruption could break entire regional populations. And there is another piece of evidence that made Toba impossible to ignore: human genetic diversity. Compared with many other species, modern humans appear to have passed through periods when our ancestral population was relatively small. Some early interpretations suggested that Homo sapiens may once have been reduced to only a few thousand breeding individuals, perhaps around the same broad period as the Toba eruption. The story seemed to fit: a supereruption, a volcanic winter, a genetic bottleneck, a handful of survivors rebuilding the human future. It is a powerful idea because it offers one dramatic cause for one apparent biological mystery. But powerful stories are not automatically correct. The archaeological objections begin in India, beneath and above the ash. At sites such as Toba in the Sun Valley, researchers have found stone tools in layers below the Toba ash and in layers above it. The tools are not identical in every detail, and dating ancient sediments is never simple, but the basic pattern is difficult to dismiss. People, or at least human populations using related stone tool traditions, appear to have occupied the region before the eruption and continued afterward. That does not prove life was easy, it does not prove Toba had no effect. But it challenges the idea that the eruption instantly emptied South Asia of humans, and India is exactly where a simple collapse story should face its hardest test. Parts of the subcontinent received substantial ashfall. If Toba caused a universal human die-off, we might expect a sharp break in occupation, a long abandonment of sites, or an obvious technological reset. Instead, in some places, archaeologists see continuity. Not everywhere, not clearly, but enough continuity to make the picture complicated. The climate evidence is complicated too. Ice cores from Greenland and Antarctica preserve traces of ancient volcanic eruptions, including sulfate spikes that tell us something major happened in the atmosphere. Climate models also show that a Toba-scale eruption could have caused cooling, especially in particular regions and seasons. But estimates of how much cooling occurred and how long it lasted vary widely. Some earlier models suggested a severe volcanic winter lasting years, perhaps followed by decades of disruption. Later work, using improved climate simulations and better volcanic inputs, has often produced a more moderate global cooling signal, still serious, still capable of changing rainfall patterns, but not necessarily enough to turn the entire planet into an uninhabitable wasteland. That difference matters. A drop of a few degrees can be deadly in a vulnerable landscape. It can alter monsoon systems, shorten growing seasons, and push food webs toward collapse. But a global average is not a local experience. One region may receive less rain. Another may become cooler but wetter. A coastal population may survive on marine food while inland groups struggle. A mountain refuge may protect one community while trapping another. So when scientists disagree, it is not always because one side has ignored the facts. Often they are asking different questions. Did Toba create a global temperature decline? Probably, at least for a time. Did it disrupt regional climates and ecosystems? Very likely. Did some human populations suffer, move or disappear because of those disruptions? That is entirely plausible. Did it reduce all humans everywhere to a tiny population of around 10,000 people? That remains contested. And did Toba cause the genetic bottleneck seen in modern humans? That is even harder to prove. Genes can reveal that a population was small. They can sometimes estimate roughly when that reduction happened. But they do not preserve a label saying, "This was caused by a volcano." Population declines can result from drought, disease, competition, migration, changing habitats, or long-term climate instability. They can also reflect population structure. Many small, separated groups may look genetically like a much smaller population when viewed from the present. The timeline is also less precise than dramatic documentaries often suggest. A genetic bottleneck dated to somewhere around 70,000 years ago might sound like a perfect match for an eruption, 74,000 years ago. But genetic dates come with uncertainty. Different methods can produce different ranges. Mutation rates are estimated, not directly observed in the deep past. Ancient populations did not rise and fall in clean, single-year events. A decline could have begun before Toba continued after it, or happened in several pulses across thousands of years. This is why archaeology matters so much. Every new site can change the map. A single stone tool beneath an ash layer can show occupation before the eruption. A dated hearth above that same layer can show that somebody returned or never left. Microscopic ash particles found far from the volcano can reveal where Toba's plume actually travelled. Improved luminescence dating can narrow the age of sediments. New methods for identifying ancient proteins, DNA and chemical residues may someday tell us which human groups occupied places where bones have vanished. The debate is not catastrophe versus no catastrophe. The real debate is about scale. Was Toba a near-extinction event for humanity? Or was it a massive eruption whose effects were severe but uneven, striking some populations hard while others endured in refuges across Africa and Asia? Right now, the strongest answer may be the least satisfying one. Toba was almost certainly a terrible event, but the evidence does not yet show that it reset all of human civilization, because there was no civilization to reset. There were only scattered human worlds, each facing the ash, the cold, and the changing land in its own way. And if a true global population crash happened, it should have left traces deeper than a legend, clearer than a coincidence, and harder to explain away. So, what would a real global population crash actually leave behind? Not a story, not a coincidence in the timeline, not just one number generated by a genetic model. It should leave a fingerprint across multiple kinds of evidence, in our DNA, in the ground, in ancient ecosystems, in the strange silences between archaeological sites. If Toba truly reduced humanity to a few thousand survivors, or even fewer, the effects should be visible far beyond the ash layer itself. Start with genetics. An extreme bottleneck happens when a population shrinks so dramatically that only a small fraction of its previous genetic variation survives. Imagine humanity as a vast library. Every person carries a slightly different collection of genetic books. When most of the population disappears, most of those books disappear too. The survivors pass on only the volumes they happen to carry. Generations later, their descendants may be numerous again. Millions, then billions, but they are all rebuilding from the same reduced shelf of genetic diversity. That is why geneticists look for several things. They examine how much variation exists across the genome. They search for long stretches of DNA inherited from common ancestors. They model how often genetic lineages merge as they are traced backward through time. They compare the diversity of modern humans with that of chimpanzees, gorillas, Neanderthals, and other species. A severe, sudden crash should produce a sharp signal. Many genetic lineages would disappear around the same broad time. The surviving lineages would converge on a relatively small ancestral population. Rare variants would be lost. Harmful mutations might become more common simply because there were fewer people for natural selection to filter through. And as the population recovered, genetic diversity would expand outward from that narrow point. But there is a catch. A genetic bottleneck does not have to mean one disaster killed almost everyone at once. The same kind of signal can emerge from a population that remains small for thousands of years. It can emerge when groups are scattered and rarely interbreed. It can emerge when one expanding population replaces or absorbs others. It can even reflect the history of the particular ancestors who contributed most to living humans, rather than the total number of humans alive at the time. That distinction is crucial. A model may estimate an effective population size of 10,000. But effective population size is not a head count. It is a measure of how many individuals were contributing genes to future generations. The actual number of living people may have been larger, or those people may have been divided into small, isolated populations that looked genetically smaller than they really were. DNA can tell us that our ancestry passed through narrow corridors. It is much less certain about what built the walls. Now look at archaeology. If a volcanic winter caused a true global reset, we might expect human landscapes to change abruptly. Regions occupied before the eruption might fall silent afterward. Tool traditions might vanish. Stoneworking methods that had persisted for thousands of years could disappear, replaced much later by different technologies carried in by new populations. At some sites there might be a clear before and after pattern. Dense layers of tools, hearths, butchered animal bones, and fragments of pigment below the eruption horizon. Then ash. Then a long interval with almost nothing. No camps, no cutting tools, no repeated visits, no evidence that people returned for centuries or millennia. We might also expect reduced diversity. Before a crash, neighbouring groups may make tools in subtly different ways. Different shapes of points, different raw materials, different methods of striking stone flakes after a severe collapse. Those local traditions could vanish along with the people who carried them. The archaeological record might become simpler, more uniform, less regionally varied. That would not prove extinction by itself. People can change technology for many reasons. A new hunting strategy, a new resource, a shift in climate, or contact with another group can alter toolkits quickly. But if genetic loss, widespread abandonment, and technological discontinuity all appeared at the same time, the case for a major population crash would become much stronger. Then there is the ecological record. Volcanoes do not only affect humans, they affect the landscapes humans depend on. Lake sediments, peat deposits, cave floors and ocean cores can preserve microscopic traces of ancient environmental shock. Pollen tells us which plants were growing nearby. A sudden drop in tree pollen, combined with more grass, drought-tolerant plants or wind-blown dust, can point to cooler or drier conditions. Charcoal can reveal changes in fire activity. Less charcoal might suggest wetter conditions or fewer natural fires. More charcoal might indicate drying landscapes, burning vegetation, or perhaps humans concentrating fires in the remaining habitable places. Animal remains matter too. If food webs collapsed, certain species might decline or disappear from local records. Large grazing animals could become scarce. Fish populations might shift as lakes cooled or water levels changed. Small mammals, birds and insects can reveal environmental changes that larger fossils miss. Even tiny chemical changes in sediments can show whether a lake became more stagnant, a river weakened, or vegetation rapidly retreated. This is the kind of evidence a true planetary disaster should leave behind, not one dramatic scar, but a chain reaction. Ash in the sky, climate shifts in ice cores, changes in pollen, changes in fire, changes in animals, changes in where humans live, changes in the technologies they use, and eventually, changes in the genetic diversity carried forward by the survivors. But deep prehistory has a brutal limitation. Absence of evidence is not always evidence of absence. A camp may have existed, but its tools were washed away by a river. A shoreline site may now lie beneath the ocean because sea levels changed. A forest camp may have left almost nothing durable. Organic tools, baskets, wooden shelters, clothing, food stores and human bodies usually vanish. Even stone tools can remain buried beyond the reach of excavation, hidden beneath meters of sediment in regions no archaeologist has ever surveyed. And the more catastrophic an event was, the harder it may be to reconstruct. Floods erase camps, Erosion mixes layers. Ash can preserve one site while destroying another. A region may seem empty not because nobody lived there, but because the evidence did not survive. So what does the current record say? It does not fit neatly with a single clean global reset. There is evidence that Toba caused major environmental disruption. There are regions where human occupation may have been interrupted, ecosystems may have changed sharply, and small populations could have suffered terribly. For some groups, the eruption and its aftermath may have meant migration, famine, fragmentation, or extinction. But there is also evidence of continuity. Stone tool traditions in parts of India appear to cross the ash horizon. Human populations in Africa show no universally accepted sign of a sudden species-wide collapse at exactly 74,000 years ago. Genetic studies support periods of small ancestral population size, but they do not identify Toba as the confirmed cause. The record looks less like one switch being thrown across the world, and more like a map of unequal survival. Some places were hit hard. Some may have emptied. Some became refuges. Some populations adapted. Others disappeared without leaving enough evidence for us to know they were ever there. That may be the real lesson of Toba. The question is not whether the eruption mattered. An event that large almost certainly did. The question is whether it broke humanity everywhere at once, or whether it exposed the ancient truth of survival. When the world changes, the future belongs to the scattered few who happen to be standing in the right place, with the right skills, when everything else falls apart. And that ancient truth is still visible today. Lake Toba is not just a beautiful lake in the highlands of Sumatra. It is the flooded scar of one of the largest volcanic events in the last few million years. The lake stretches across the landscape for nearly 100 kilometers. In its center sits Samosir Island, an enormous block of land that rose after the eruption as the ground beneath the caldera slowly pushed upward again. It is a place where catastrophe became scenery. People live around its shores. Farmers work the surrounding hills, boats cross water that fills a basin excavated when an unimaginable volume of magma blasted out of the earth 74,000 years ago. From the ground, it can be hard to grasp the scale. There is no single smoking cone towering over the lake. No obvious crater wall announcing that this was once the source of an eruption powerful enough to spread ash across continents. But the volcanic system did not simply disappear when the eruption ended. Toba remains part of an active volcanic region. Sumatra sits along one of the most geologically violent boundaries on Earth, where the Indo-Australian tectonic plate is being forced beneath the Eurasian plate. That collision feeds the chain of volcanoes running down the island. It also produces frequent earthquakes, hot springs, geothermal activity, and constant movement deep below the surface. Active, however, does not mean about to erupt. This is where the story often gets pulled away from science and into apocalypse. Toba is regularly described as a supervolcano, a word that immediately creates an image of a countdown clock. Headlines ask whether it is overdue. Videos claim the next eruption could happen tomorrow. Some turn Lake Toba into a sleeping monster, waiting for the right moment to erase civilization. But volcanoes do not work on schedules. A giant eruption in the past does not mean another giant eruption is imminent. The fact that a volcanic system is still capable of producing earthquakes, heat, or ground movement does not mean it is preparing to repeat its most extreme event. Scientists do not predict supereruptions the way they predict an eclipse. They assess changing probabilities. They watch for swarms of earthquakes that may indicate magma or fluids moving underground. They measure whether the ground is rising, sinking, stretching, or cracking. GPS stations can detect movement of only a few millimeters. Satellite radar can map subtle deformation across huge areas, revealing whether a volcanic landscape is changing over time. They sample volcanic gases when they can. Changes in carbon dioxide, sulfur dioxide, or other gases can offer clues about pressure and heat beneath the surface. They track hot springs, lake chemistry, thermal activity, and changes in local seismic patterns. In Indonesia, monitoring agencies combine these signals with geological fieldwork and hazard maps because the goal is not to announce the end of the world. The goal is to give people time, and that matters. Indonesia is home to more active volcanoes than almost any other country. For most volcanic hazards, the real danger is not a hypothetical supereruption. It is the far more frequent threat of ashfall, landslides, lava, toxic gases, earthquakes, tsunamis, and fast-moving flows of hot gas and rock. These events can destroy communities even when the eruption is nowhere near the scale of Toba. So the responsible lesson is not, Toba will happen again soon. It is that rare events do happen. And when they do, they expose every weakness in the systems people depend on. A major eruption today would not confront a world of small bands moving between scattered refuges. It would confront a world of 8 billion people connected by shipping lanes, power grids, satellite networks, industrial agriculture, and supply chains that cross oceans every day. A few degrees of cooling in one region can reduce harvests. A failed monsoon can affect hundreds of millions. Ash in the atmosphere can disrupt aviation, contaminate water, damage machinery, and block sunlight. Food shortages in one country can become price shocks in another. A climate disturbance does not need to be globally identical to become globally dangerous. That is the modern version of the Toba question. Not, could one volcano instantly kill nearly everyone alive? Probably not in the simple way popular stories imagine. Humanity is too widespread, too numerous, and too technologically capable for that kind of clean ending. But could an extreme volcanic event trigger years of agricultural stress, economic disruption, migration, political conflict, and regional famine? Could it hit a world already strained by war, inequality, ecosystem loss, and climate change? Absolutely, and Toba is not the only deep-time risk. Large eruptions are rare. So are major asteroid impacts, abrupt climate shifts, pandemics with unusual properties, and failures cascading through tightly connected global systems. Their rarity can make them easy to ignore, but rarity is not impossibility. In geological time, the impossible-looking event is often just the event that has not happened in anyone's lifetime. The humans who lived through Toba, if they lived through it in the numbers some theories suggest, did not survive because they understood volcanic aerosols or global climate models. They survived through mobility, cooperation, local knowledge, luck, and the simple fact that they were not all in the same place. That gives us perspective, but it does not give us certainty. We still do not know exactly how cold the world became after Toba. We do not know which populations suffered most, which refuges held, or how close our species came to disappearing. We cannot turn an ancient eruption into a precise forecast for the future. What we can say is this: Lake Toba is proof that the planet has the power to change human history without asking permission. It is a reminder that civilization is not the same thing as security. And it leaves us with a question that is far more urgent than whether 10,000 people survived 74,000 years ago. If the world changed that fast again, what would keep us alive now? Maybe the most honest answer is also the least dramatic one. Something enormous happened 74,000 years ago. That part is not in doubt. The youngest Toba Tuff eruption was real. The ash layer is real. The caldera is real. The volume of material blasted into the atmosphere was staggering. For people living close to Sumatra, it was almost certainly a catastrophe beyond anything they could understand. Landscapes were buried. Rivers and forests were disrupted. Food webs changed. In some regions, the sky may have darkened, rains may have shifted, and seasons may have become less reliable for years afterward. Toba did not need to kill every human on Earth to change human lives. A small hunter-gatherer population can be pushed toward disaster by changes that would barely register in a modern city. A failed rainy season means fewer edible plants. Fewer plants mean fewer grazing animals. Fewer animals mean failed hunts. A river changing course, a coastline shifting, a forest burning, or a familiar migration route disappearing could turn a successful territory into a trap. And if those stresses continued across multiple years, the effects would compound. Children would be the first to suffer, elderly people, anyone injured, sick, or separated from their group. Small populations have very little margin for error. Lose a few adults with specialized knowledge, the person who knows where water lasts through drought, which roots are safe to eat, how to make a particular tool, and the consequences can last for generations. So yes, Toba likely created serious environmental disruption, especially in South Asia and Southeast Asia, where ashfall and regional ecological damage may have been severe, and possibly much farther away, through climate effects that altered rainfall, temperatures, and seasonal patterns. But that is not the same as proving that Toba nearly erased humanity. This is where the famous number comes in. You may have heard that only 10,000 humans survived. Sometimes the claim is even more extreme. One story says humanity was reduced to a few thousand people. Another says a single tiny band of survivors hid somewhere in Africa while the rest of the world died. It is a powerful story. It is also much more precise than the evidence allows. The number comes from genetics, but genetics does not provide a census list from 74,000 years ago. It does not tell us that exactly 10,000 people woke up one morning after the eruption and found themselves to be the last humans alive. What genetic studies can estimate is something called effective population size. That is not the same as the total number of living people. It is a model of how many individuals were successfully contributing genes to future generations. A population can have thousands, or even far more, actual people while producing a much smaller effective population size because of unequal reproduction, separation into small groups, population structure, and repeated local extinctions. In other words, 10,000 survivors is not a photograph. It is an interpretation, and even if our ancestors did pass through a population bottleneck around this period, genetics alone cannot identify the culprit. A bottleneck could reflect drought, disease, migration, long-term climate instability, fragmented habitats, or multiple disasters arriving over thousands of years. Toba is an obvious suspect because it happened at roughly the right time, and because its scale was so extraordinary. But obvious is not the same as proven. The archaeological evidence complicates the picture even more. In India, stone tools appear below and above Toba ash deposits. That does not prove that every local population survived without hardship. The people who made those tools may have changed, moved, declined, or recovered. But it does show that the human story was not necessarily a clean before and after line, with total absence below the ash and a new world above it. There may have been continuity in Africa too. There is no universal archaeological signal of sudden human disappearance at exactly 74,000 years ago. Some regions show stress, some show adaptation, some may have been buffered by coastal resources, wetlands, rivers, or flexible social networks. Humanity was already spread across varied environments. A volcanic winter, if it occurred, would not have hit every place with equal force. That may be the central fact of survival. There was no single humanity standing in one field beneath one darkened sky. There were separate groups, different landscapes, different food sources, different skills. Some may have been devastated, others may have moved. Others may have endured through local knowledge, cooperation, and luck. A disaster can be global in origin while being intensely regional in its consequences. So what really happened 74,000 years ago? The most defensible answer is that Toba was a colossal eruption that probably caused profound environmental disruption and may have added severe pressure to already vulnerable human populations. It may have contributed to population decline in some places. It may have reshaped migration routes, resource strategies, and the fragile networks linking small groups across Africa and Asia. But we do not have proof of a single event reset. We do not have proof that exactly 10,000 people survived. And we do not have proof that Toba alone created the genetic bottleneck seen in our species. What we have is something more unsettling than a simple apocalypse story. We have evidence that humanity lived through a world capable of changing faster than culture could explain it. A world where ash crossed continents, climate may have faltered, and small populations faced pressures we can only partly reconstruct. And if one crisis this large can leave so many unanswered questions, imagine how many others are hidden from us. How many droughts erased entire communities without leaving a recognizable ash layer? How many epidemics passed through prehistoric populations and vanished without a trace? How many migrations, famines, floods, and regional collapses changed the course of human evolution, leaving behind only broken tools, scattered bones, and gaps in our DNA? Toba is visible because the earth preserved its scar. Most ancient disasters did not, and that brings us back to the people at the center of this story. Not humanity as an abstract number on a graph, not a neat line of ancestors marching through prehistory. Real people, small communities of mothers, fathers, children, hunters, gatherers, tool makers, elders, carrying memories of water sources, animal paths, edible plants, and dangerous seasons. Somewhere in their world, 74,000 years ago, a mountain exploded with a force almost impossible to imagine. For people near Toba, the eruption may have arrived as a nightmare without warning. The ground shaking, darkness in the sky, ash falling onto forests, lakes, rivers, and campsites, animals fleeing or dying, familiar landscapes becoming unrecognizable. They would not have known the name of the volcano. They would not have known that ash from the blast would travel across vast parts of Asia, or that scientists tens of thousands of years later would find its chemical fingerprint locked in layers of earth. They only knew that their world had changed, and farther away beyond the thickest ashfall, other groups may have experienced the disaster differently. Maybe not as a single terrifying day, but as a series of bad seasons. Rain that came late, cold that lingered, plants failing, herds shifting their routes, rivers becoming unreliable. A landscape that had fed people for generations suddenly demanding new decisions. Do we stay? Do we move? Do we share what little we have with another group? Do we risk crossing unfamiliar territory in search of food and water? Those choices may have mattered more than any single invention, more than strength, more than numbers, because the survivors of a crisis are not always the biggest groups or the strongest individuals. Sometimes they are the people who can change their habits before it is too late, the people willing to eat different foods, travel farther, form alliances, exchange knowledge, and abandon a place their ancestors had called home for generations. That is the deepest lesson of Toba. The eruption proves that the natural world can transform human possibilities in an instant. Toba was real. Its scale was extraordinary. Its ash blanket is one of the clearest geological timestamps in the recent human past. It tells us that people living across parts of Asia were confronted with an event capable of disrupting ecosystems on a massive scale. It also plausibly suggests something else. Toba may have intensified the pressures already facing small human populations. It may have damaged regional environments, disrupted food chains, altered rainfall patterns, and made survival harder in places already vulnerable to climate change. In some areas, it may have caused local population crashes. It may have forced migrations, it may have broken old networks and created new ones. And it may have played some role in the long genetic story that eventually produced the low diversity seen in modern humans. But this is where the unfinished question remains. Scientists still cannot confirm that Toba alone caused a human bottleneck. They cannot confirm that exactly 10,000 people survived. They cannot identify one hidden refuge where the last humans waited out a volcanic winter. They cannot look at a genetic signal and say with certainty, this was the eruption, this was the year, these were the victims, and these were the survivors. The evidence simply does not work that way. DNA records population history in broad, blurred patterns. Archaeology preserves only fragments of daily life. Climate records vary from place to place. Ash layers can tell us an eruption happened, but they cannot tell us what every family did when the sky turned grey. That uncertainty is not a failure of science, it is the nature of deep time. We are trying to reconstruct a human crisis from stone tools, sediments, chemical traces, bones and genes passed down through nearly 3,000 generations. Every new discovery sharpens the picture, but every discovery also reminds us how much has been lost. Maybe Toba was the Great Reset. Maybe it pushed our species to the edge and only scattered communities endured. Maybe it was one devastating chapter in a longer story of climate instability, drought, migration, and repeated local disasters. Or maybe the truth lies somewhere between those possibilities. Toba was catastrophic but not universally fatal. It wounded human populations unevenly. Some groups disappeared, some declined, some adapted. Some may have barely noticed the global event at first, only to confront its consequences months or years later. And some survived because they happened to be in the right place, near a dependable river, along a productive coastline, beside wetlands that held water when the surrounding land dried out, in a region where edible plants remained available, within a social network large enough to share food, partners, tools, and information. Luck matters in survival, but luck alone is rarely enough. A group that finds refuge still has to know how to use it. They have to cooperate when stress makes cooperation difficult. They have to care for children through hunger. They have to pass knowledge across generations. They have to make choices with no guarantee that any choice will work. That is what our ancestors did, again and again. They moved. They adapted. They learned. They formed bonds beyond the immediate campfire. They survived not because they were untouched by catastrophe, but because human beings had already become remarkably flexible creatures. And that flexibility is still written into us. Every language, every tool, every migration, every community built in a difficult place carries a faint echo of those ancient survival strategies. The people who lived through Toba, whether they faced its ash directly or endured its distant ecological consequences, were not passive victims of a changing planet. They were problem solvers in a world that offered no easy answers. Maybe that is why the Toba story remains so powerful. It is not just a story about a volcano. It is a story about how close a species can come to disaster without disappearing, about how fragile human populations once were, about how much of our past depends on small groups making impossible decisions under pressure, and about the fact that even now, with all our science, we cannot fully answer the biggest question. Did Toba nearly end us? Or did it simply reveal what humanity had always been, scattered, vulnerable, adaptable, and far harder to erase than anyone would expect? What do you think? Was Toba the trigger for a true human bottleneck? Or was it one major disaster among many pressures shaping our ancestors? Leave your interpretation in the comments and tell us where you are listening from. It is always incredible to see how far this conversation travels. If you enjoyed this journey into one of prehistory's biggest mysteries, please like the video, subscribe to the channel, and share it with someone who loves ancient history, archaeology, and unanswered questions. And if you want to support the channel in the best possible way, listen on Spotify. The link is in the description because the story of Toba may never be completely finished. But every new layer of ash, every stone tool, every fragment of ancient DNA brings us a little closer to the people who endured when the world changed around them.